All right, we are back, and I am back with Adam Block, who is our substitute teacher for today. Not to say that he is any less. In fact, to me, he is more because me and Adam, we could probably talk for like centuries on various topics. He's just one of those guys that you just want to quiz the living snot out of him, and I love the fact that you do spend the time with us. And I was going to bring you back for a different talk. We're still going to do that. So I do appreciate you very last minute spending the time to do this particular talk with us. So
Sure.
thank you, thank you, thank you, thank you. You're saving my life as usual. So for those of you who do not know who Adam is, I highly suggest that you look at some of his work. But something tells me that you're going to do your own biography right now, isn't it?
I could mention something about who I am if that is not well known. Sure, absolutely. Yeah. So should I start?
Go for it.
Okay. So as Simon mentioned, yes, I was given word that it might be something that could unfold. I give a presentation in 2 days' notice. So here I am, 2 days later. What that means is what I'll be presenting today is it is contemporaneously, just off the cuff here. And as such, it won't have that nice prepared kind of look to it, though some of the material is stuff that I cover in other places, and I'd like to highlight where some of those other places are, because it'll give anyone out there watching opportunities to see more of this material that I make available in various kinds of forms. So my deal is that I, over the past couple of decades, have put together some public outreach programs at large observatories, including the National Observatory Kitt Peak, and then subsequently, back in 2007, I founded the Mount Lemmon Sky Center for the University of Arizona on top Mount Lemmon, which is just very close to where I live here in Tucson, just north of me. And so through these public outreach programs, one facet of that activity, it's not everything, it's just one part, is the work that I've done with astrophotography through all of those years, using these telescopes to do public outreach and to generate what I hope are compelling images for various kinds of purposes. I also develop materials that explain and teach how to take data, astronomical data, and put it together to create the images like the ones that I typically enjoy publishing. So that's the basic thing. I've also been fortunate to do some other things where the images have been published in other places, like Astronomy Picture of the Day and in magazines. In fact, for some time, I was a columnist at Astronomy magazine, and I got to also share some of these techniques about astrophotography and some of the ways in which you can approach the rendering of images through that particular medium, which I thought was really exciting. So that's a little bit about my background. As far as today is concerned, what I'd like to do is highlight a few things that, one is kind of an update, which is just fun for me to do. So I'm going to do that right off the top. I'd like to demonstrate a technique for de-emphasizing stars in images. This is an innovation that I created some time ago, but there's an update for it that makes it even easier to do, and I'd like to highlight that. Then I'd like to show some things that are relevant to CMOS users, actually. That is the biggest thing right now, is that everyone has or wants to get a CMOS camera. And there are some slight vagaries. There's some variations in what to look for, what to look at, what to set as far as the parameter space is concerned when processing CMOS images. So I'm going to show some examples that aren't necessarily CMOS specific, though there are a few. But it's really, I will try to put it in the light of CMOS so that you can see where some of these differences are and what to look out for, especially in terms of problems. Some of the information that I am going to demonstrate here has been garnered from user groups where people post their problems, and then I look at the data and I go, oh, okay, here's what's going on. So those would be some of the examples that I would like to demonstrate today. So that's the broad stroke of it. I do have I will say that I have a website, of course, that I have information Part of the information, obviously, people pay for. There's just hundreds and hundreds of hours of videos in which I explain how to process images. My main emphasis these days is PixInsight, though I've covered other software programs, including obviously Photoshop and CCD Stack, if anyone still remembers that program.
Yes, I do still remember that program.
Very nice program for what it does. And on another note, there is also a website that I just post my, astronomical picture. So if you want to follow me there, that's a good place just to see when new images are released. Most recently, of course, is the comet. It was very difficult to take a picture of it from here in Arizona because it was never very high in the sky from here. And right now, this is our monsoon season, which means rain or not, generally not raining, but almost always cloudy. Making it very difficult to take pictures of things in space right now. So I had to travel quite a good distance to the west of where I live in order to get this picture. And finally, and I think that this is the one that's really relevant, especially for today, this is something that I'm trying to really bring up, that's kind of new for me, is to make my presence on YouTube a little bit more active and more effective, I guess. So I'm posting videos today. This is effectively free content, though I would ask that you check it out, right? Some of the stuff that I'll be doing today is from this information. And it's really nice when people will follow or subscribe or comment on or like or whatever it is, these videos, because it gives me some reason to believe that someone's looking at it. I don't really need to see it myself. This is really for other people. So if I know that other people are watching and there's an audience out there, that really helps me to stay motivated to do this stuff. And the one video, these are just some videos, among other things. Not only will you see astrophotography, you may actually see me playing table tennis, which is one of my other pastimes. At least
Let's do a quick to watch. I want to see
quick
this.
Watch.
Yeah, come on, show us.
All right. I have no idea what's going to happen here. So I'm about to serve the ball. This is probably coming across very choppy.
It doesn't matter.
There, I killed it. Did you see that?
Yeah.
Okay.
I love it, man. You've got the headband, the whole 9 yards.
Well, you need the whole 9 yards, but that's a different sport. So this sport of astrophotography, what I'd like to show right now is this idea of de-emphasizing stars in images. This is the video, but the main reason I'm going to bring up the video right now is right at the end, I put up a summary screen. And on the summary screen, it has the directions. There are basically 7 steps. And like one of the steps is just make a copy of an image. So it's really simple to do this technique, but it's really powerful. So I hope that you'll give it a try on your own data where it is appropriate to use this particular technique. So the image that I'd like to do this on is one that I've brought up here. This is the kind of image that you would want to potentially de-emphasize the stars. Here is an image where the field is filled with lots of medium and small kind of bright stars. There are some just large bright stars, and those are fine, but those are not as prominent as all of the multitude of other stars that are kind of just distracting. Now, we don't necessarily, not for this technique, want to remove the stars. That's very different. We can just make them go away. But instead, we want to do something a little more subtle. We want to de-emphasize them so that the nebula itself remains much more prominent and easy to see, and it's less distracting by all this other stuff. That's the fundamental idea. Typically, the technique that's used is based on an erosion filter that tries to shrink the stars based on neighboring pixels. And instead, I tried to figure out a way to do completely away from that particular technique and another way to approach this problem entirely. And so you'll see what I came up with. Now, let me show you the history of this particular image so you can see this. I already did the deed here, but I've gone back in time where this is right after I created an LRGB combined image here. So there's really no processing that's occurred. We just have kind of a color image. I did histogram transformation, which basically makes it a permanently stretched image. And then I renamed it to be LRGB, indicating it is my LRGB image. That's all that's taken place on this particular color image. So let's look at the instructions here and see what the first step is. The first step says to make a copy of the color image that you're going to work on to de-emphasize the stars and give it a special name. The name we're going to give it is going to be substitute pixels, because that's the nature of the technique. Instead of looking at neighboring pixels and using an erosion filter, we're actually going to substitute pixels using another, coming from another image, a substitute pixel image. That is the idea. And we're going to take advantage of the tool StarNet to make this an easier process. So let's do that first step here. Am I there? I am there. So I already did make a copy. Here it is. This is the clone of this image right here. Nothing special has been done. And then we're going to use StarNet++ to create a starless version of the image. So in this program, I have StarNet++, but I'm going to save some time. So I would run it on the image here and create a starless image that, of course, we're going to give it that name that I said, subpix, because this will be our substitute pixels. But to save time, instead of running it, maybe I just destroyed it. Yeah, of course I did. So I will run it. And while I'm running it, let me show you what this technique looks like if you look at it in detail. So let's go here. There we go. So on my website, under free videos, I actually have it completely annotated in a written way, not just in video form, but in a written form here. And what I'd like to demonstrate is here's where I'm doing the part that we're doing right now with StarNet++ to make a starless image. If you want, I created this technique before I was using, before StarNet++ was even kind of a thing. So you had to create a starless image using another means. And the means by which you do it is you create a star mask, and I do that using MLT. So you create on that image what looks like a star mask. You use binarize to make them firm looking stars in that mask. So that's what binarize does here. Then in all of those positions, after you maybe dilate it a little bit, here you dilate, at all those positions you run MMT to remove the stars. I note that StarNet++ is done now, but I'll get there. It did it faster than I can explain the old method. You remove the stars, and then you put, you can blur it here, but then you put noise in the place of where you remove the stars with noise generation. And now you've matched the regions where you remove the stars with exterior regions. StarNet++ does all of this for you. So all of these steps just to create a starless image, it's very powerful, because with StarNet++, I only get one answer. It's what it is or nothing. With this methodology that I'm showing here, I would encourage you to check it out, because the technique itself is powerful, even if you don't use it for this purpose. The idea of generating a star mask and removing things from an image using MMT and so on, that's all very, very powerful. But all of those steps are simplified here when we use StarNet++. And we can do multiple versions of how to do that if you're doing it kind of in this manual way. So here we are, we have our starless image, and we will call it that cool name, subpix. So now going back to here, let's look at the instructions. The instructions say, on the original color image, we're going to make another copy. Actually, they're going to make two copies. One is going to be the grayscale luminance. We'll call that Loom. And the other one is going to be called halos, because that's what we need to generate to substitute these pixels around the star and effectively shrink them a little bit. So let's go ahead and do that step here in PixInsight. PixInsight is here. whenever you are going to be extracting illuminance from a color image, it's usually a good idea. It's probably not important here, but it's usually a good idea just to run RGB working space. You set these all to 1, and this way we are creating a luminance which isn't biased towards one particular color or another based on this color space. So you just run it on it, and then we create a grayscale image. This one I'm just going to call Loom, and we'll just have it. We'll need this later. I'm just generating it now. Yeah, I already have it because I've done this before. I'm going to call this Loom 1. I've obviously done this thing before. Okay. And then we need to create another one of these things. And this thing I'm probably going to call Halos 1 because I'm sure I have a halo somewhere too. There we go. So do you agree with me that we now have our original image and we have kind of 3 things running around here? We have a sub-pix, that's our starless image. We have a luminance image, that's just going to stay here. And the one we need to work with, I'm going to minimize, that's the old one here, sorry. And the one we're going to work with for a moment is the one we're going to call halos. This is the one where we need to create the star mask. So the easiest way to create a star mask from, in this case, a grayscale image, a lot of people go to the star mask process. You don't need to. Why? It takes so much time. All we need to do here is generate a mask that basically captures most of the stars in the image. Not all of them, but most of them. In fact, a natural question might be, if I'm creating a star mask right now, why didn't I just use what StarNet? I can have it output a star mask for me as well. But I don't actually need or want all the stars. Every single star would not help me. We really just want the majority of them. Those are the ones that are distracting, the medium kind of bright stars especially. This technique only works if you can shrink the stars to begin with. If your stars are already undersampled, if you're using an image where the stars are 1 pixel, you can't shrink them anymore. They're 1 pixel. There's nothing you can do. So this is kind of a good example where the images, the stars are small, but they're greater than a single pixel. So de-emphasizing the stars can work out well here. All right, so using MLT, basically we just specify what layer do we need to keep that keeps stars, and everything else bigger than that layer, we just call not a star, or at least not representative of a star that we're interested in de-emphasizing. So as a good guess, the first 4 layers it's about right. Now, if you want to be really clever, you can even get rid of the first layer here. You can do this, but it doesn't matter for our purposes here. So you just run this here, and now we have something that looks like a star mask, but notice that things in this image have different grayscale tones based on how much they are represented in each of these layers. So a big star like this looks very dark gray because it's not represented in the first 4 layers very well. It shows up a little bit, but not really. Whereas things that are considerably brighter here show up much more because they are representative of that scale size. So we can use that to our advantage by using binarize here. When we use binarize, we're going to make things either solidly white or solidly black. And something like this star, if we click on it here, I can see what the reading is. It says 0.12. So that might be something below which we want just to not include. A medium bright star here is 0.5. Well, that's easy. Here, this star we would like to include, that's 0.4. What about this guy right here? 0.3. What about this one right here? 0.16. So as a compromise, we are going to get a lot of stars, I bet, if we do something like 0.2, because 0.2 will include a lot of things. Now, it won't include the very smallest ones that probably wouldn't help us anyway. And it's going to exclude the very biggest ones. So I'm going to put 0.2 here and watch what happens. So now we have a lot of stars in our star mask. We don't have the very huge stars because we're not going to be able to shrink those in any reasonable way. And we don't have all the tiny ones, but we have lots and lots of middle bright stars. What's next here? So we just did this. We used MLT, excluding all layers not representing the small, medium, bright stars, generating a quick star mask. It says apply a healthy dilation and small convolution to this halo's mask. Okay, so that means that we're going to dilate this using morphological transformation. I think I can move this, right? Oh, good. Yeah. I don't know if I have it open or I can't see. Do I have it open? I'm going to go get it. So morphological transformation is here. Now, we need to dilate this star mask large enough that it might leave us room to do multiple iterations of shrinking the stars. If I only enlarge it a little bit, because we're going to be covering the stars in a moment in the real image, then we won't leave ourselves any room to shrink any more if we want to. And I'd like to show you at least 2 iterations if you'd like. So I'm going to dilate on the order of 7 in terms of elements here, this size 49 elements, 7 dilation, and we'll grow what we see here quite a bit. Now, it is nice maybe just to put a little bit of a fuzzy edge on it. So you can always grab convolution. And 2 is probably fine, just to make them a little bit fuzzy like that. And then it says, after we've done that, we want to subtract the loom from the halos to create this halo's mask to create the actual halos. This is the most powerful trick. This is the clever part. This is the thing that, well, this is one part of it anyway, that really makes this technique work. So we have here's our white blobs, which are where the stars are. And here's an image that also has stars and lots of other stuff. So if I take this image and subtract this from it, if I subtract this thing from the halos here, things that are very bright that aren't represented here are going to be subtracted from black regions. So anything that's in this image that's in a black region will just make it even more negative, which will just remain black in the mask. You don't get, there's no representation for negative values in an image. So nothing will happen there. The only places where something happens are where there are stars here that overlap these white blobs. And then you're going to see, of course, halos, because those are only the stars. So we'll get out pixel math, which should be, I don't know where my things are here. I'm going to go get it because I don't know where things are. So we go to pixel math, and we're going to take halos, I guess 1, minus loom 1. Does that sound right? And what you get are halos. Isn't that cool? But these are special halos. These halos are special in the sense that the black areas in the middle, they're of course protecting the cores of stars. Typically, when you use an erosion filter, the cores are not protected, especially in very small stars, but you'll see even in the smallest stars, there's still a little bit of a core. And that protects that central region, which makes this method, I think, an improvement. In addition, the profile of brightness, if you will, the inverted profile of the star that's subtracted here to make this halo, it precisely matches the star itself in the noise, in the profile of brightness. It's an exact match. And that also makes it very good for doing this technique because you have exact matches of stars here. Now, if you thought that these halos needed to be brighter, we don't want to smooth them because they do have that match of noise and everything else. But you can, if you wanted to, make them a little brighter. So for example, if you just, using histogram transformation, if you just make them a little brighter, that doesn't hurt anything if you just want to make this effect of pixel substitution stronger. Now, once we have the halos mask in hand, I'm just going to make these a little smaller here. We can apply this to our original image as a mask. And if you zoom in and we look around here somewhere interesting, maybe we zoom in here. If we actually show the mask, you can see where we have the halos here surrounding these stars. So that looks good. And then what we do is we write our starless image, and I called it subpixels, right? Subpix, what did I call it? Subpix.
Yeah, subpix,
Yep.
PIX.
You write subpix into here and watch what happens. Did you see it? It was fast. Let's undo it and redo it. Do you see what happened to some of these stars here? Watch. Before and after. Before, let's zoom in even more. Do you see how they shrunk a little bit? Simon, tell me you can see it so I know that.
Oh yeah, no, sorry, I'm
okay.
more actually amazed by it because.
Okay, good. So it's very, very subtle, but you'll see that it shrinks down a little bit, right? And what we're doing here is not an erosion. We are actually substituting values that are coming from subpix into these halo regions. So that's the cool part of the trick. Now, you might say, well, I want to do more. I want to do it again, right? Well, let's zoom out and see just how subtle this is. This might not come across, I think, in Zoom, which is compressing stuff and whatever. But let's see, here is the before and the after. Can you see how it lessened the multitudes just a little bit? Didn't touch any of the bright things, just the multitudes of all the medium, bright, and faint things, a little bit. But if you want to do one more, here's what you do. You're no longer going to use this luminance. Instead, you're going to create now a new luminance because these are shrunk a little bit. So we need a new luminance to work with. So we just extract another luminance here, like that. So this will be now our, I can call it again Lum 1, doesn't matter. Lum 1. There it is. Now we need to redo the mask, though, in the sense that we dilated by 7 last time. This time we are only going to dilate by a little less because now the stars are a little smaller. That's why you needed to go a little bit larger to begin with. So I'm just going to back up here. There's our brightening. Here's the fuzzy. There's the dilated. That's the original mask there. So what we can, I don't know, do I have it? Yes, I have it. Good. So now we can just do 5 if we wanted to. So I go like this. We apply it here. Probably don't have convolution. I'm going to keep going and getting it because it's faster than me trying to find it. Again, you can do this. You know what? I think that's probably a lot. Let's do 1.2. Let's just do a little less there. There. Now we're happy. I'm happy. Okay. And then we should subtract halos 1 minus Lum 1. Sounds right? Right? I'm not going to bother to brighten it. I'm just going to go ahead and apply here. It should already be applied. So now we can do another iteration. Let's go look again at some of these stars here. Now I'm going to concentrate like on this guy here because I want you to see something. We're going to apply it by doing the substitution like this. Did it do it? I missed it. I either did something wrong or image not found because it is subpix. There. So you'll find that on the majority of the stars, we went yet another, here it is to begin with, 1 iteration, 2 iterations. Now what you'll notice is that on some of these stars, it shrinks far enough inward that it does create something of an artifact, especially if you're doing more than 1 iteration of this. Though if you zoom out, you probably wouldn't tell, but I'll show you how to fix that as well. So here is no iterations, 1 iteration, 2 iterations. Any more than this, and you're really just going to start erasing the stars. So, and we're trying to de-emphasize them, not erase them. So let me show you one last thing we can do here for this second iteration. All I'm going to do is back up here. Remember, here is the mask before we dilated. What we could do in this mask is just be sure to remove some of the very largest stars to begin with. So what I'm going to do is just make a copy of this here, and I'll call this big stars. Big stars 1. Yes, I know, I've done it. At least I'm consistent.
True.
And then what you can do is you can use closing. The way closing works is that it looks for things at a scale, a structuring element size that you specify. So we're going to basically shrink everything down at I'm going to pick a scale here of 11. So we're going to shrink everything down. Anything that is less than 11 pixels in size will be shrunk all the way to 0. So you'll end up with a black bit. It'll just be black. There's nothing left. But if you have a structuring element of 11 and you had something that was 12, 13, or 14 pixels, whatever, you have a little bit left over, the parts that are left over are going to be blown back up to the same structuring element size, in this case of 11 or so pixels. So you'll have this, all you'll have are the things that were larger than that threshold, basically. So watch what happens when I apply here. I'll zoom out a little bit. Most of the stars here have disappeared. These are basically just the very, largest ones. If I thought that this was too, if that was too much, we could lower this to 9. I don't remember what I actually did, but, and this will have maybe a few more stars, something like that. If we want to be a little safer with what's left over here, we can dilate this by maybe 5 or 3 or something, just to be sure that when we do our subtraction, it'll really subtract from here. So let's do that subtraction now. All we do is we take halos minus big, that's probably halos 1, minus big stars 1. That sound right?
Mm-hmm.
And then watch what happens to the bigger stars. They go away, right? So here they are before, here they are after. Now, again, I'm only going to be operating on the smaller stars. So we come back here, we do our dilation again, because I went back in time, right? So we do our dilation of 5 this time. We do our convolution of whatever that was, 1.3 or something here, right? We do a subtraction of halos 1 minus loom 1. Yes. Here are halos. Now we apply this to the original here, which should be applied because I still have it linked, but I'll just force it. There it is. It's applied. And then finally, we can do this time our second iteration. Now let me zoom. I want to be sure I'm not on my second iteration here. You'll see that no, this is only one iteration. So I'm about to now do the second iteration here. Let's zoom in to find that same star there. This star was the one that had problems on the second iteration, and now it doesn't. Although maybe you can argue this one does. So you can maybe reject more stars. But that's how you can protect larger stars, medium stars, from showing any of the ill effects of the technique. And then if we zoom out, you get the overall effect. So here's none, 1, and 2. That's the update for the star de-emphasis in getting it to go. Before I continue, because what I'll do next is completely different, are there any questions out there, Simon, on this or something related?
Not yet.
Okay.
I think people, this is typical. What happens is, because even I'm like, it's not a case of we being lost. It's a case of us like, that's what we've been doing wrong type scenario. Well, not necessarily.
No,
I got to ask you this though.
Yeah.
How the hell do you come up with all these things?
Okay, so here's the thing I really want to get across, Simon, and this is the thing that I hope, I need motivation in some sense.
Mm-hmm.
So this is why I hope people will support me and visit the site and visit the YouTube videos and so on. I am not going to just explain stuff. I mean, that's fine, and I enjoy doing that. But I literally want to come up with new ways of doing things. And I think that I've been consistent in doing that through many years. There are many other techniques that I developed in Photoshop and other places. But now in PixInsight, I bring that same desire to find different and new ways of doing it, mostly from experimentation. This really is the result of having a set of techniques, like the idea of MMT and MLT and so on, but putting it all together to use it in a different way. So the answer to your question is that's how. It's by knowing what I wanted to do. I didn't want an erosion filter, and I thought, there's got to be a way to get other pixels in there rather than just using neighboring pixel values. And I know how to do this, this, and this. Hey, so I can do what I want. That's really the idea. And that's why I could really use some support out there for continuing to try to come up with these creative things.
So what do you want them to do? Give you weird ideas or weird
No,
problems?
I don't need I need people to subscribe to my YouTube channel and consider buying my videos tutorials. That's what I need.
Yeah. Oh yeah, well that's a given, I think, as far as I'm concerned.
Nothing is given in this world. So okay. Yeah, if there are no other questions, then I'm going to continue with actually what is another innovation, but it is related to CMOS in a way. So I am going to create a new project just so, let's see, is that the best way to do this? Load empty project, that should do it. Yeah, that's fine. Good. What I'd like to demonstrate is the idea of selective rejection. One of the interesting things about CMOS imagery is that the cameras tend to be very low noise. And in addition to that, the bit depth on many cameras, they might be 15-bit or 14-bit cameras, so that you can't expose for very long. And again, either because of low noise or because of this need of not saturating the signal, you take very, very short exposures and you add them together, integrate those images together to do your work. But by virtue of the fact you have short exposures, a number of things become more important than they would have been, like if you did longer exposures with a CCD camera. And it's that thing that I'd like to point out now. One of the virtues of having lots of pictures is that rejection of, outlying values or of transient things going on in images works very well because you have a large sample size. And so I'd like to demonstrate kind of the idea behind being able to control that if you can't otherwise figure out a way to do it. You can't do it mathematically, you can force the issue, and that's what I'd like to demonstrate here. So let me show you an issue. Here I have data of M88, and if I do star clear star, here are some of the luminance images of M88. Here's one such image. Looks pretty good. I mean, there's nothing going on in this image. It's a very nice calibrated, flat fielded image. Everything is good. This would be the kind of thing that you want to add together and just go along your merry way. But if you look at an image like something that may have transpired on April 15th, and I'm just going to take a stab here, one of these images. Do you see how, for whatever reason, the flats were not as good, and I'm left with let's call it a goober. I'm left with a thing in the image. Now, the thing in the image, the data that I took across a couple of nights, across 3 or 4 nights, this would only represent 1 night's worth of data. I might have, I think I had 5 or 6 exposures here. And it's only a fraction of the subset of all exposures. If this thing existed in every single exposure, what I'm about to show you doesn't work. This only works when you have a problem that is in some fraction of the much larger set. And when you have that situation, you can use this technique, and it's just really great. This dust donut, if I were just to straight up integrate the images, I will save you from watching that occur, will not reject out. It just won't, because these values just aren't bright enough. They're down in the noise. You will see that dust donut in the final result if I just integrate all of my luminance together. So that's a problem. And this could be a problem if you have a lot of images that may have some issue that's faint. It's something that just will not, like a satellite trail, or it could be some cameras, I don't know if CMOS has this so much, but some cameras have a RBI, where you have this residual image showing up somewhere, and It might only occur in a certain small fraction of frames. That maybe you have some amp glow that for whatever reason didn't get rejected in certain images, or it didn't get calibrated in certain images, but in other images I did. So some fraction of images have that problem. So this applies to CMOS as well, but you have a large number of images to work with. So let me demonstrate what you can do. I'm going to open up the problem images here, and then I'm just going to integrate them all. That's what I'm going to demonstrate. So these images that I'm opening, they are already registered. They are already calibrated. All I need to do is just combine them using image integration. So let's do that again. Star, April 15, star. So here they are. Now I have I only want the clear. So I have a handful of them, but it doesn't take too long. If I were clever, and I'm not going to be clever now, I am clever in some of my other videos, you can use a image container and a process container to operate on all of these images at once, but I'll just demonstrate this without doing that. What I need here is something called a paint bucket. So I will literally call this paint bucket. And I'm going to use this to paint on these images in just a moment. Getting out pixel math, we're going to make this image, which is the same size. I just made a copy of one of these images. I'm going to make it completely, entirely, 100% black. So now I have a paint bucket. That's something to use. Here is one of the images, and I notice this image has a little bit of something down here at the bottom. Before I get any further, let me show you what I'm taking advantage of here. If we go to image integration, you'll notice that once you have picked your rejection method, you know, and I don't know, maybe I'll use Winsorized here. You can choose to clip a low range. This means that whatever value you specify, and you specify it in the next panel right here, whatever value you specify for the low range, anything at that value and beneath are rejected without even doing any math. They're just not used. And when I say not used, it means that if I have 5 images where I have some values that are not being used, in those places when it does image integration, we will only be averaging the other 15. So we won't have any of the effect of whatever was going on in the 5 images, and we just take the average of the other 15. This works out extremely well when you have a large number of images. You won't even be able to see by eye the difference. If you only had 7 images and you were removing 4 images in this one location or some values or something, well, now you're only left with 3 images to average. And by eye, you'll be able to see the difference you won't see the problem thing, that'll get rejected, but you'll see the difference in the signal and noise between the region where you're only averaging 3 pixels compared to the region where you're averaging 3 values compared to the region where you're averaging 7 values. So this technique works well when you have data where it's only a small subset, but you have a large set of images. So we're going to get out, that's what I'm taking advantage of here. We're going to get out our clone stamp. I'm going to make well, let's see, click on the target. That's the target. This is my thing. Do a radius of 99, whatever. The hardness, we want it to be completely hard, no softness. And then you, let's see, selecting target point. You basically just paint like that. You see how careful I was? That's it. And you go, okay. And then these images I'm going to need to save, of course. But I just basically use so the source, the target. Oh, see, I made a mistake. I don't care. And I paint. Now I got to be careful that, let's just do this again. So the target, so I got to click in the middle or else I can't paint. There. So I think you get the idea, right? So I click my source, my target. Why do I keep doing that? I'm an idiot. Yeah, I'm gonna keep doing that too, aren't I? Let's see, let's do this. I'm doing this very poorly. There we go. But it'll only make it better because, you know, I'm making a mess of it. There we go. Target, source, paint, check. So we do target, source, paint, check. Target, source, paint. Two more. I'm having fun though. So we have target, source. Oh, come back here. Paint. Really careful stuff. Now, usually you only have a problem in a few images, right? So we do target, source, paint. But I did an extreme. Now let's say, I don't know, maybe I didn't like this thing either, you know, so you could target, let's see, so I have to what, start somewhere here, source. So you could do this too. There, that's close enough. I'm not gonna worry about it. Get the idea. So these images I'm going to save. Now I need to be a little careful about how I do this. Let me think about this for a moment. See, I created a directory here. So what I'm going to do is I will just delete my old ones just so I can show you, or maybe not. Maybe I'll just make a new directory. This is what happens when you're live. I'll just make a new directory. File, save as. So I'm going to call this what? Wood Hills. Fine. So we're going to do save, right? Yeah. So I wonder if I can do it. Let me just save these things. Oh, I don't need the paint bucket. Maybe I screwed up on the other one then. There might be one in there that I'm not doing right.
While you're clicking furiously and saving, is there a way to do, so if we read the question, if the images are registered and the artifact is in the same location across multiple images, is there a blah, blah, blah?
Yes, that's what I was saying. You can just use, I'm not going to demonstrate this because I didn't want to make it complicated. Right. But you can use a combination of a image container and a process container if you needed to do this. Yes. And then it can just apply to the same places in each of the images. I hope I'm doing this right.
Only you know the answer to that right now.
I'm doing it so fast that I'm sure I'm making all kinds of mistakes here, but we'll find out in one moment. File, save as. Okay, and then I made it. I know I screwed up on one. I didn't save one of them because I ended up saving the paint bucket instead. But
yeah, it doesn't matter.
Whatever. I don't know what this.
Yeah, let's just kill that.
No, that's okay.
Oh, that's the big satellite streak.
Yeah, sure. I can keep that. Okay, so although I need to know which number. That's an L because that was not one of the April 15th for whatever reason. I got that one in there. So that's L4 plus the April 15th. Okay. So here's what we do. We're going to add the files, right? We're going to add, what directory am I in now? Here, calibrated, light, cosmetized, registered. All right, here we are. So we have star, clear, star. So here's all the clears, right? But we're going to add all these together, except we're not going to use these ones that say 15 that are clear. We're not using those because those are the ones that I just adjusted, right? Those are the ones I just saved them in a separate place. So I don't want to use these guys because those are the ones I just made with my little marks on them. Does that make sense?
Yep.
Okay. So I want to open those. I also want to add, let me think. No, I think that's fine. That's it. So I'm going to add the other files that we made our little adjustments on. And then everything here is going to be integrated together. That's the idea. So as far as a sigma value is concerned, 2.5 is usually good. Sigma low, I'm not going to worry about. The cutoff is fine. As long as we have the range low here set to be 0, that's the key to making this work. So it isn't the only key, though, and I'm going to get back to it. This should work as is, but it's not for a reason that's a little bit subtle, and I'm going to demonstrate how to fix it. So this is why I got so excited when a particular capability became available in image integration. Originally, image integration didn't have this, but then this capability you'll see at the bottom here of the screen that's called large-scale pixel rejection. What that does is that for any region where there is any pixel where it's a rejected pixel, you can specify kind of an amount based on the scale size, the multi-scale size that you work with wavelets. You can specify how much to basically grow that around the region where you've already rejected some pixels. So that growth is going to help us solve a particular problem here that you'll see. So it's integrating now. Just give it one moment to show me the final result. Here it goes.
So while we're waiting for that, question here is, does your star reduction technique work with undersample stars, or would erosion be better?
Well, I don't, my personal opinion, it's going to end up with the same thing. Erosion is actually going to make pixel-like stars just disappear. Now, that may still give you the effect that you want. You may actually want lots of those pixel-like stars to basically disappear.
Go away, yeah.
Go away. But it's not because you're shrinking them. You're just literally making them go away. So the technique that I'm demonstrating will also make them go away in the same way. I don't know that you're going to notice a very big difference between the two techniques in that sense. You'll notice it only when you're trying to really shrink stars that are kind of medium-sized, 2, 3, 4 kind of pixels in size, where you can make actual halos. Because once you're down to a single pixel, it's just 1 pixel. What are you going to do? Or 2 pixels. There's nothing you can do. Now, there is a trick, though, if you want. You can upsample your images before you apply any of these techniques. And in the upsampling, of course, you're generating more pixels. And so then you can take advantage of the technique and then downsample again, I guess. But that gets, I don't know if that's tedious or not. So I'm going to remove these. And this is the integrated result. And what you'll find is no problem. This, by the way, this is a very deep result of this galaxy. These images were 15 minutes each, and I don't know how many I combined here. How many?
A lot.
Yeah, 30, right? So that's like 7 hours worth of data or something like that. That's pretty darn deep. And you'll find that the dust donut doesn't show up, but check it out. If you look closely where we did some of that rejection up here, let's see, can you see this? It's kind of hard to see.
Yeah, no, we can see it.
Yeah, let me see if I can find, you can see the boundaries. It's not sure, yeah, you can see the boundaries of where I drew some of my things. I actually have enough frames that the boundaries don't stand out well. Let me go down to the bottom here where I only did 2. I can't remember where it was though. Well, the boundaries don't stand out that much in this case, but there are some boundaries there. And that has to deal with the fact that when you draw the black pixels on the images, there's an interpolation that happens at the very edge of where you did the clone stamp. And so they're not actually totally black. And so they get left, and they're not rejected, and they get left as part of that rejection process. And you'll be able to see these patterns of where you're rejected. Now, I would argue that by eye, everything in here compared to everything out here, in here we have like 6 or 7 less pixels being averaged together. So out of 30, out here or in here, we only have 25 or 24. Out here, we have the full 30, right? I can't tell by eye that there's a difference in noise there. No way. But I can see this weird garbage. So to get rid of the garbage, what you do is you employ large scale rejection on the low end. And that grows these little regions just a little bit so that it'll be black further out. And then you don't get that result. So let me just go ahead and run this. Let's see, I'm going to do that there. So I'm just going to run it again. The only difference is I turned on that large, low scale growth. And I'll blink it with this image, and we should see, I hope, this is what happens when you do it live, that that artifact goes away. So let's just give this a moment here.
How long have you been using PixInsight for now?
Well, one of my roads to using PixInsight began back in, I think about this, 2014? Is that right? What is it? 2000? Yeah, it's
2020. 6 years now.
Yeah. So probably 5 years, between 5 and 6 years ago. I got to remember which July it was. Because of my prevalence in creating video tutorials, especially for Photoshop and at the time CCD Stack, people, PixInsight was just starting to ramp up back then. There were workshops going on in 2014 and 15. And people wanted me to develop content for how to use PixInsight because everyone wanted to try to learn how to use this software. But I didn't know how to use it at that point. And so I did my best by trying to attend a workshop or learn from example, or really just sit down and learn it myself, which is the main thing that I did. And it took me basically 4 years to get to a point that I felt that I had a firm kind of grasp. So the answer to your question is, I've been using it since 2014 or 15, but only at a proficiency that would allow me, I think, to innovate and perhaps explain things probably since 2018 or so. I felt really comfortable with understanding, I think, a lot of the workings of the program. So that's where it is. But it's been a long, I really didn't want to do anything until I had a much firmer understanding of how everything works.
Oh, I kind of wish you didn't close that integration layer down with the crap.
So you wanted to see it? Yeah.
Yeah.
You would have seen my, sorry. You would
Yeah.
have seen the things that I had drawn. You should have said that earlier, man.
I just spotted it. I was too busy listening. It is what it is.
So if I do this here, now I've matched the two. It is my hope that that this pattern here, which again is very hard to see, goes away here. That's it. So the garbage that you see in one, can you dimly see the thing here?
Yes.
Okay, and it goes away here because of the large scale rejection. It does a complete rejection. Let me see if I can go to another place where, can you see the curve that's
here?
Yeah,
I can see all of that. Oh my gosh.
Okay, so I'm going to match these two. And now because of the large scale rejection, it should, I don't know that that's real, but the other parts get rejected away.
Yeah, don't flick around too quickly because obviously the spottilization from the, there we go.
One, it's really hard to see it too.
No, I can see it.
Yeah.
I mean, that's because I know what I'm looking for too.
Yeah, but I probably could have made the growth even a little bit more to make sure, but whatever. Even if you didn't do it, even if you didn't do this last little thing, the basic idea of selectively rejecting by painting on a picture, that's really the important point. And if you're left with artifacts, that's how to fix it. So I showed the fundamental aspects of using this technique of selective rejection.
Now, obvious question that I'm going to ask here, well, may not be obvious, is when you were doing that clone stamp painting,
Yeah.
everything had a harsh edge. What if those edges were feathered? What
No,
difference
that
would
would be
that make?
bad. That would be bad because in image integration, when you're specifying the low range, you're saying this value, and I only had one value there. I had 0. Only if it was 0 where I painted would it be rejected. So if I have something that is non-zero, a feathered edge would mean it would be some combination between what the data was, the value, and where you painted, right? That's going to be above 0. So it wouldn't be rejected, and you would be left with real weird things at the edges of where you painted. It would be bad.
So remember that.
Yeah.
I only wanted to, I asked that on purpose because I can see people's heads thinking of, oh, if you can get rid of that problem just by feathering. I'm like, no, you can't.
No. This is taking advantage of selecting based on rejection based on a threshold, and that threshold needs to be a hard threshold because you're specifying what the threshold is.
Hope you guys understood that, because I obviously did. That's why I asked it, just so people could understand it.
Okay. Now, we've been about an hour. So I have 3 kind of vignettes that deal specifically with CMOS kind of detectors. But in order to explain some of this, what I'd like to do is go over one of the important ways in which you interact with PixInsight in particular in the beginning, is you process the images. And these days, most people process using some batch pre-processing method like WBPP is the script that people use to calibrate their data initially. And of course, that's where a lot of problems crop up, because in the course of processing data, there are lots of these vagaries, especially with regards to CMOS chips, that become important where it wasn't necessarily as important or it would have been important in a different way for a regular kind of CCD sensor. So that's what I'd like to demonstrate next. And in order to do it, I need to set up a visual kind of picture of darks and flats and biases and all of that. So do we need to take a 5-minute break, or shall I just march on?
You can just plow on.
Just plow on? Okay.
Yeah. I mean, if you need to go to have a break, that's entirely down to you.
No, I've just learned that when you do these marathon things, it's a good idea to take a break. How many people are watching at the moment?
We got about 50 or so.
50. That's pretty good. Okay. So here we go. As a visual way to picture calibration data, I created this silly thing here in Photoshop. So maybe I should mention that what WBPP looks like. So here is the script for WBPP. This is what it looks like. And you end up loading the calibration data that you're going to be using, and of course the data you're going to be calibrating. So you have these tabs to load your biases, your darks, your flats, and of course your lights. And what I want to highlight here specifically are a couple of checkboxes. Checkbox 1 that is very important that people understand the behavior of. It's this box here where you calibrate flats with darks. What is the difference between having this checked and not having it checked? It's very important to understand that. Another one is over here, optimize dark frames. What is that about? And then finally, there's another checkbox that people want to touch and you don't really want to unless you know what you're doing, which is this calibrate. Yeah, I know, I'm not meaning to. Calibrate master darks thing. What is that about? Those three checkboxes cause all kinds of problems, whether you have it checked, unchecked, oh my goodness. But if you understand the nature of the flats, the darks, the biases, how that is related to CMOS sensors and so on, a lot of that mystery becomes much more elucidated, much more clear, and it's not a problem. That's what I'd like to work at getting to the point of. So when we take a picture of the sky using a sensor, well, maybe I'm going to do this. I'm going to do it the other way. let me let me not take a picture of the sky. We have our chip, we have our sensor, and we just take a picture of some infinitesimally small exposure time. What we'll end up with is not a picture of zero, but we'll end up with a picture of something. Now, what we call that thing is a little bit tricky. For the moment, I'm going to call it a bias level. It's basically the electronic level, the number of electrons that are in the sensor. That's what you're downloading. And it has some characteristics to it. But it isn't light, of course. It is just a level of electronic or voltage that you have on your sensor that needs to be subtracted from data eventually. If you take a longer exposure, and the amount of time that's necessary for this to happen depends on your sensor, whether it becomes significant or not. But if you take a longer than a single infinitesimally small exposure time, there's an additional effect. The additional effect is that because of the temperature of the chip or the electronics of the sensor, more electrons gather through time. And that gathering of electrons is a kind of signal, often called the dark current, because this is a dark frame. So a dark frame that is 0 seconds long is a bias frame. I mean, you're not capturing anything collecting. Nothing has had time to become significant in any way. But when the exposure time is long enough, you may be gathering more of these electrons, and that is what we would call a dark current. A dark frame then is a picture of the bias plus any additional stuff that may have added through time. So that's very key to understand. A dark frame is a bias plus extra stuff, unless, of course, the dark frame is the same kind of infinitesimally small exposure. Then you basically have something that looks like a bias. So that's where you begin, and that's what I'm trying to indicate here, where we have maybe in our bias tab, we have a bias. So this is that little blue thing represents an amount of signal, an amount of bias, an amount of voltage, whatever you want to think about. A dark frame then is the combination of that thing plus some extra stuff that may be added through time. And then a flat field image is a picture of some light source, right? It could be a panel, could be the twilight sky. Generally, it's very short. So typically, a flat field image would contain no dark current because there's no time for anything. If you take a 100th of a second exposure, a half a second exposure, 3-second exposure, the dark current in that time that you took the flat is almost negligible, may probably be entirely negligible. So I symbolize that here by saying that a flat field in general, unless you have very long exposures, which might be true for narrowband images, but in general, if you can make your light bright enough, you just have the bias, whatever that is, plus all that light that was falling on the chip. And then a light frame of the sky, of something you're taking a picture of, has all of this. It has the bias. It may have some dark current because the exposure was long enough. And then, of course, it has the signal from photons that were actually hitting the sensor. So these items then, the red and the blue things, are what we subtract from the data before we do the calibration. Now, what I'm not showing here is how the division happens. When we calibrate this data, we need to subtract this stuff off first before we divide by the flat in order to truly calibrate the fundamental light frame that we're working with. But if we don't get this subtraction right of the bias and the dark and so on, the flat fields don't work. That division process doesn't work. So when you find that flats don't work in a particular way, it's usually because there's something wrong with the bias dark thing going on here. And that's what I want to demonstrate in some data that I have some examples of here. So let me bring up and this is what live is terrible. Let me bring this up here. So if you recall, I'm just going to flick back here. There's a checkbox here that says Calibrate Master Darks. Ay caramba. So typically, what happens is when you load dark frames, you're going to have a whole bunch of them here. In fact, I'm just going to go ahead and do that. I'll clear this, right? And if we add dark frames, I don't know where I am. Let's see, I'm here. So I can just add some darks. I'm sure I have dark frames somewhere. Do I have them in this directory? Maybe not. Let's go somewhere where I have some dark frames. Maybe I just have darks somewhere here. These say they're darks. Yeah, there's some darks. Okay. So when you load a bunch of dark frames here, what happens is when you load them in WBPP, it is going to use image integration to combine these darks and make a master dark. If you don't already have one, when you load the raw darks here, you're going to make a master. And then that master, which is basically what one of these things are that I've been showing in, these are kind of like masters. I'm not looking at a raw. You could talk about one file, I guess, but imagine that these are masters. So you're going to create a master version of a dark and a bias and so on to be used when you load them in here as raw frames. But the trick is it just uses image integration. There is no fancy, there's no other mathematical operation that's occurring. You are literally just averaging these frames together to create the master. And what that means is if a dark frame has a bias in it, which I just showed you right here, a dark frame has the bias. If we just average them, we had a whole bunch of raws in here and we average them together, we're still going to have the bias and we're going to have the dark current. So that becomes important because there are some operations where WBPP needs to know that you actually have given it this thing. Now, I have an aside, an opinion. I don't know why anyone would want to give WBP a master dark that is not simply integrated. Why are you going to make life so hard on yourself? Oh my goodness, drives me crazy. But you can. You can manually create your own darks. You can subtract the bias on your own and then bring it in here. So instead of seeing this thing in the column, what you end up with is something that looks like, now this is going to be hard, that. If you give WBPP this thing, and then WBPP is going to try to subtract the bias from the dark before it gets used, you will have double subtracted the bias. That's bad. WBPP is expecting it to still have the bias frame. That's the whole point of this little checkbox. This checkbox is saying, calibrate master darks. That's what I'm expecting. Yes, have it checked. By default, it's checked. This is what WBPP is expecting. It's expecting this thing to be in this form. If you bring a dark frame in here, and I still don't know why you would do this, but if you bring an already integrated dark into WBPP and it doesn't have the bias, then you need to uncheck this crazy box. Then it will behave properly. WBPP will behave properly. If you double subtract a bias, the flat won't work because you, and then, by the way, you'll subtract too much information. It makes a mess of the end result. So that's
Hold on.
Yeah.
Is this more specific if I was to create my own master frames?
Yeah. Yes, that's exactly right.
Okay.
And which is why I'm arguing this is supposed to be a batch process. Why are you doing that? Create the masters in WBPP, simply integrated, and then use those simply integrated masters here with the default configuration as I've described with the calibrate master darks being checked, and then everything will behave correctly.
I see why some people might have that problem now. Is I've seen numerous tutorials in certain situations where they show you how to create these calibration frames.
I know. And if you're doing it all manually, that's perfectly fine. That's no problem. And by the way, if you can keep track of what you did and you understand what's going on, there is no problem. This doesn't break the system at all. The authors of WBPP made it flexible enough that you really can bring it already bias subtracted darks and everything is going to work out fine. But the problem is that many people, especially I would say new users who are trying to get their handle on getting things to work, they have mixed, these two different ways of approaching calibration, because you have to understand what the expectation is of this script is. That causes a lot of problems. So that's why I'm spending 10 minutes to explain that idea. You want to, in general, I think what's easiest is just create the masters here, keep that checked, because that's what it's expecting, to have master frames, a master dark that has the bias.
I think I need to drag you back to do a class on calibration frames alone. I think it's a huge stumbling block for a lot of people.
What I've described, though, is probably 50% of it. Because
well, yeah.
there's only two things to subtract. You only have two subtractions. You're subtracting a bias and you're subtracting a dark. That's it. Though there's one other stumbling block, which is what I'm going to relate next, and it is related to this idea, which is that this guy here. So let's see.
Oh, wait, you got to turn off that top layer. Go up 2 layers. Yep, that one.
That's okay.
Yeah.
So you'll see that people also get confused, I think, with optimized dark frames. What is that about? Well, optimized dark frames is the idea that when we have a dark frame that looks like this, what happens, let me see if I can explain that properly. Do you see how this light frame, my dark current over here, the red bar matches the red bar here. So this would be a matched dark frame that I would subtract from the light frame, right? So everything is perfect. It's going to subtract these two bars will be completely subtracted over here on the right, and there's no problem at all. Everything works out in the course of calibration. The problem happens when people give, let me see if I can find this. Oh, this is going to be tough. Let's see. No, that's the lower one. This one's the hard one. Oh, here, maybe. Yes. Yes. Now, I don't know if that's this. So if we had this situation, if you have a dark frame that is longer in time than the light frame, that's what this looks like. The bias is still the same, but it has more dark current, right? I can't directly subtract this thing from this thing over here on the right. The bias will subtract correctly, but the dark current here, there's more of that than there is in the light frame. So the way optimization works when you have this checked is it's going to subtract the bias from the dark, because we have this thing checked, because that's what it's expecting to do. This is why you would want to make sure that this is working properly. And then it scales this red stuff to equal that. It finds what factor it needs to multiply this red thing by to make it equal this, and then it does the subtraction. That's what the optimization is doing. PixInsight has a very nice iterative way of measuring based on noise and whatever, how to compute that factor. But it does it. And so you can actually take longer darks, even if the darks were the same exposure time, by the way, you can use optimized dark frames. So even if I was back in this situation, you can still use the optimized dark. You can use it in this situation that I have checked here. Here's a but, though. The calculation for computing how much red stuff we have over here compared to here, especially when these numbers are small, can lead to errors. You may not get the correct factor. And if you don't get the correct factor, then this subtraction will not be perfect. And when the subtraction isn't perfect, the flat field doesn't work right. And again, you're left with a problem. So my suggestion is the following. When possible with CMOS users, and I'll explain why this is important in the last part, why this is important specifically for CMOS, but especially for CMOS, I would say in general, but especially for CMOS, it's very good to begin by not having the optimize thing checked. Let me see if I can find that. I suggest do not optimize the dark frames. Make sure you're matching your darks for both your lights and your flats. That won't do any harm. Optimize may give you a slightly better answer, might, but you will always get it to work, or it should always work if you're just matching the time and temperature and everything just matches exactly. If you can get that to work, then you can experiment and check this box and see if you get an even better result. But if you're matching to begin with, not doing longer exposures and all that kind of stuff, just matching everything up, and you get that to work, then you know that the sensor is behaving properly. You know that your technique for using the tool is correct. You know the data is consistent and correct. Everything is working correctly, basically. So I recommend using without the optimization thing to begin with. Then if you want to work your way into optimization, understanding the reason or how it's working by calculating this factor, then, fine, it's great. The problem that people have is that the optimized dark frames, let me demonstrate this, ready? If I hit reset here on WBPP and I click OK, guess what checkbox is checked? As a default, optimized dark frames is checked. That can lead to problems. It leads to problems because if it tries to optimize on dark frames where there may not be a bias, or there may not be much dark current because CMOS cameras don't have very much dark current, you end up with a bad result. So my suggestion is don't run into that problem. Just try to begin by doing exact matches of your data, darks subtracted directly at the same time from the flats and from the, so you're making what are called flat darks, and from your light frames, matching darks, so that everything works okay. In fact, I'm going to pause right here and demonstrate exactly my point, I think. So let me, let's see, I will clear this because I don't know where I am now. Yeah. Oh, this might actually be it, but I'll just start from scratch here. So I'm going to add some light frame files here. Add lights, there we go. And I need to go to, let me navigate here, hold on. Let's see, this is video recordings, PixInsight, WBPP, no, fundamentals, WBPP. Although I should mention that what I'm about to demonstrate is available here. I have a series on YouTube that is a, can I go to playlists? Yeah. Mm-hmm. So I have what I'm explaining to you now, I've set out in a very nice way in a, where is it? Collection. There it is, the first one here. I think it's an 11 or 12 part series. 10 part series, sorry. Thought it was more. That explains all about WBPP. So I would highly, and it's available to everyone. So I would highly recommend go visit this, please, and watch everything. And it explains just as I'm trying to do now, but much better because it, I'm not live.
Under pressure.
Yeah, under pressure. So here are some frames. These are light frames. I'm not going to do them all here. I'm just going to highlight a fraction of them or something. So those are some light frames. And then this is derived from a question that came on one of the forums. The guy was saying, I can't get this to work. I can't get my dark frames to subtract correctly. What am I doing wrong? It's a typical kind of problem. In fact, it was couched in a different way, which seemed much more mysterious, but the actual answer was much less mysterious. So he provided darks, but I believe I made a master dark. So I think you'll agree with me that I can just generate a master dark by simply integrating. This is what I did. So there's the master dark, and here are the lights. Now this particular person didn't provide anything else. No biases, no flats. That's it. He has data. He has lights and darks. So I am going to exit out of here for a moment. And let me, no, we're close. So, and that's not it either. 1 second. I got to navigate there again. So that is here. PixInsight, here, fundamentals, here, here. So this is what the data looks like. And it's with a CMOS camera. In fact, it's the ASO. If it's the ASI something, we can probably look here at the Fitz header, probably tell us. Do you see it anywhere, camera?
What are we looking for?
The camera.
Oh, who makes the camera?
Well, it's the ASI. There's a particular model. I don't remember which model this one is. That's all. Oh, here it is.
Yeah, there it is.
Yeah, 1294 MC Pro. There it is. So that's the camera this comes from, and you'll see that there is. Do you see the amp glow here in the raw data? And there are lots and lots of these kind of hot pixels running around in the image. So this has not yet been debayered. It's a picture, what apparently is M94. So we have hot pixels, and we have, what you would expect to get an amp glow in the raw data, right? So that's what I just loaded here in the script. That's all I have are some light frames and the dark. And the point is that when you do it in this manner, here is the default settings. People, they use the default settings, right? So I'm going to, what am I going to do here? I am going to do the following. Yeah, I'll just demonstrate it in this way. So let's just make an output directory. Temp, that sounds like a good place to make an output directory, right here. So let's be sure that we're doing everything correctly here. I think so. If I hit diagnostics, it's going to complain that I have no bias frames and I have no flat frames, and I agree. So all it can possibly do is subtract a 122nd dark from these, a master dark from these lights. Do you agree with that?
Yep.
Okay. Now, what I don't agree with is the following. What I don't agree with is I probably have some junk in there right now. So.
Okay, somebody just put a question out there. I'm going to wait till you're done because this one's going to take a second.
Yeah, one second. One second.
Yeah.
Let me just be sure. Oh, master. No, not master. Sorry. Lights. Where's oh, real run? Oh, I know what I'm doing. Put it in temp. Good. Yeah, sorry. This gets very complicated very quickly. So I'm going to delete. Actually, I don't think these matter so much, but I will delete these. Delete these. Okay, I'm doing this fresh because I had more files in there. That's all. I'm going to run this, and then you can tell me. Yeah, go ahead. All I'm doing is I'm calibrating these. I'm just subtracting the dark. And this is done from default settings. So what the main point that I want to make here, in addition to CMOS stuff, is that the idea that defaults are good or reasonable or correct or more effective is an illusion. Defaults are an illusion. You can quote me on that. Okay, go ahead, ask your question.
There's two questions here, and I'm going to have to backtrack on this one just in case. It says, do you know of a Photoshop plugin that does this effect? And he's talking about the star reduction.
Yes, though it uses an erosion type method.
The next question, and this is where it gets complicated. I have two ways of answering this, which is kind of odd. What's your opinion about calibrating without using bias frames? I've found that it works much better than when using them with my 071 color camera, we'll call it. It makes no difference what camera you own, actually.
Okay, that's the final thing I'm going to be demonstrating. It does make a difference. And the reason that you're finding it makes a difference or it's not working is because of the stuff that I'm about to say.
All right, I had a feeling about that. That's why I was like thinking, I'm not going to.
It's very much related to the idea of how CMOS sensors work in general and so on.
Beautiful.
Okay, So I simply calibrated these frames and look what has happened.
Yay.
It didn't work. Look, you have the amp glow here. You have the little hot pixels running around look at all those little color hot pixels everywhere, right? It didn't work. And it didn't work very well because we used the default settings. We had checked optimized dark frame. Now the dark frames matched, but it still ran the routine to try to optimize. And it ran the routine. It doesn't even have a bias frame. How the heck is it going to figure it out? It doesn't have anything to subtract from. So it just tries to figure it out based on the noise characteristics. And it comes up with a bad answer. This gentleman tried to do it this way. And he ran into this problem because of the fact that that was being checked. So my suggestion again is make sure things work when they're matched. And the thing that I want to really highlight here is that the amp glow, that is a feature of many, not all, but many CMOS sensors that have this effect. And you want, obviously, you have to get rid of that or else that weirdness goes all the way across the frame. So I'm going to now run it again. And all I'm going to do, watch me carefully, it's like a magic trick. All I'm going to do is uncheck the one, but you see my hands? I didn't do anything else. All I'm going to do is uncheck that one box, right? And I'm going to run it again. Oh, I have to specify the same place. Hold on. Here. It's just going to overwrite those files that I just made. There we go. And then I'll open up one of those calibrated files and hopefully show the difference. And this is just illustrating this idea of understanding when to use and when not to use, and certainly what to look for as far as optimized darks. As long as you understand that optimized darks means you're changing that scaling factor in order to subtract the dark current. If you either don't have a lot of dark current or you're not handling the bias correctly, which is in this case, then you can get wrong answers. So now I will close this, go like this, open up one of these files, display it, and the amp glow is gone, and a majority of those hot pixels are gone, and everything subtracts correctly because I've matched things. So far, so good? Mm-hmm. Okay, good. I want to make sure. I can't see the screen. So. Excellent. Now, here is the creme de la creme. I am going to show you a really excellent example with regards to a set of data. Let's see, how do I want to do this? I am going to do this with, again, WBPP. I'm going to, I guess it doesn't, I would have thought it cleared everything. Okay. So as you know, let's see. We're not going to use optimization. I don't have a master dark because I haven't loaded anything. I don't know what's going on. So I am going to load a set of data where we have actually a complete set of data. And this person took the advice that I mentioned. So let me think about where this is. Hold on. This one is in here. Here it is. Okay. So this is another CMOS example where we have darks. We have flat darks, which we're going to use to calibrate the flats exactly. So there's no optimization going on there. And then we have also the data itself. Now, I don't think I need to load everything here. I'm just going to load some fraction of things. So let's do, I don't remember which button I pressed. So I'm going to add files so that I can do that without, I can add a whole bunch of them at once, basically. So back down here to Wanda, here we go. So here are a bunch of darks there. Here are a bunch of flats there. Oops, that's not what I wanted. That was neat, but not what I wanted. Okay. There's a bunch of flats. Here are darks, red flats. These are the light frames that I'm doing here. And then these are the flat darks. These are the dark frames that are going to calibrate the flats. No biases. So here's the thing. When you're matching, remember the picture here, when we match exactly a dark frame to either a flat field image or a light frame, if you have an exact match, then everything will subtract basically perfectly. So a flat dark then is a dark frame for a flat that we're going to subtract, from this flat field image. There's a weird thing though about some, not all, but some CMOS sensors, which is that they don't have a dark current. But what they do have, not in a few seconds, anyway, not a significant one in a few seconds. Most people take their flats, there might be some fraction of a second. So there's no dark current there. But what CMOS sensors do have are electronic signatures, which is that the amp glow itself is nonlinear with time. The amp glow, for example, if you did a half-second exposure or you did a 2-second exposure, for some sensors, and I've really been spoiled, it has tainted my view of CMOS sensors that some sensors really misbehave and do really weird things. So the methodology that I employ then, I just consider CMOS sensors all like this weirdness. And it's not true. Not all of them are, but there are some that do this, that you need to really pay attention to how you're working with, biases and flats and darks and so on. So my suggestion for CMOS, to make sure that things make sense and that electronic signature of amp glow and other electronic things that are going on that are in addition to the bias level, if you don't want to call it the bias, which is an argument, then you need to capture that exactly and match it with your flat data. So you create a flat dark. See, I wouldn't call it a dark frame though. I would call it a flat electronic signature frame, not a dark frame, because you're not really capturing dark current. You're capturing all this other stuff, this electronic signature, which I think is a better name. But you can match it exactly. And so that's what this flat dark is. That's why we're not going to be using a bias, because that bias is effectively that electronic signature that varies with time. See, when you use a CCD camera, you can take a 1-second exposure or a 500-second exposure, and that bias doesn't change. That electronic signature doesn't change. But with a CMOS detector, some of them do. So you got to be careful. And that's why you can not use the bias. Don't use the bias with some CMOS sensors, and just match these electronic signatures with your flat, regardless, whatever that exposure time was. If you did 1.08 seconds, you have to take a flat dark of 1.08 seconds. Because if you did 1.09 seconds, that electronic signature might be different for these CMOS sensors that do weird things. Got to match it. Okay, so that was the point that I wanted to make that goes back to that gentleman's question. Could have been gentlewoman, I don't know. That person.
The guy.
Yeah, I thought you said that, but didn't want to assume. Okay, so I'm going to load these frames here, and you'll notice I'm not using a bias. And let's see, so I have flats, I have darks, I don't have a bias, I do have light frames. So I have everything that I need here. I'm not optimizing. And what I want to explain at this point is a very particular behavior which deals with this checkbox now. I want to explain how Calibrate with flat darks works when you have them, and what it does if you were to uncheck this box. So I illustrate this in the tutorial. I'm not going to go through it now because there just isn't enough time, but I illustrate this on my online series in YouTube, where you have the case of, well, let me explain, where you have the case of having biases and then you can take advantage of them. So When you have this thing checked, it says calibrate with flat darks. What this means is WBPP is going to look in here in the darks section, and it will match, only match, the exact times with data. So if you had here for a flat, if your flat field image was 2 seconds, and in your darks, you only had 180 seconds, which is what I have here, it will not subtract 180 seconds from your flat. It just won't do it at all. It won't do anything. That's what happens when you have this checked. When you have calibrate with flat darks, the behavior in WBPP says it is your obligation to make sure that you have a matching dark loaded in the darks tab. Your obligation. I'm going to fix this fact because this, well, let me just pause and show you what happened. Remember when I loaded the data? Look in the flats here. Notice that it loaded my flat darks in my flats column. This happens to have been, this is another error that people sometimes run into and they don't realize it. This particular person accidentally acquired the flat darks as flats, so they didn't change them to be a dark. You need to be sure that the program that you're using to collect the data understands that you're collecting a dark frame, not a flat field image or something like that. So these frames here that should have been flats are actually the darks. So I'm going to clear them. I cleared them all. I was supposed to clear selected, not clear all. It doesn't matter. So all I'm going to do here is load these. Remember right here, these are the flats. But when I load those extra frames that should have been darks, you can do custom here because the person unfortunately made the flat darks. Here are the flat darks, but they were called flats. So I'm going to force it to load them as darks by being sure that the image type here is dark frame, and that'll be sure to put it in this column. So binning is probably 1. Exposure time, that needs to match 1.08. There we go. Now it's in the darks tab. I have my flats in the flats tab. And now it'll do the exact subtraction. Because now I actually do have a 1.08 second flat dark to calibrate my flats with. It wouldn't have worked a moment ago when I only had 180 seconds in this column. It wouldn't have worked. So, in fact, I would have seen an error when I tried to run it. And let me just, I should demonstrate that.
I'm going to pause you for 1 second before you do that.
Yeah.
This is actually an interesting part here that you're mentioning dark flats.
Yeah.
And it's a
flat darks. I hope I
flat darks.
That.
Sorry,
yeah.
Flat darks.
I know.
I've noticed a lot of people don't actually know what it is, don't actually do them, and bypass it entirely.
So what I'm indicating here is, and this is the important key, that CMOS detectors, some of them, have electronic signatures that are not uniquely characterized by a bias frame. You really got to record that and understand that particular thing, because electronic signatures for some, I'm not saying all of them, but for some sensors can change with exposure time. So there is no single bias frame you can take. That means you need to match a flat dark with a flat image in terms of exposure time, because that electronic signature changes a little bit with some detectors.
Right. So, but that's where the problem starts, is most people do not know what the process is to create that dark flat.
Oh, well, the dark flat is a dark frame. So you take it like a dark, but you just match whatever the exposure time was of your flat. So if your flat you took was 1.08 seconds, you take a dark for 1.08 seconds. Or if it was, I mean, this particular individual must have taken panel flats and it had it compensating to figure out what the proper level is. That's how it came up with some weird number of 1.08. But you match it when you create your flat dark. You match that time. And that will match whatever the electronic signature, whatever that CMOS sensor was doing in that time. It'll be an exact match so you can calibrate the flat data.
So hopefully that clears that up for some of you guys out there. I know it's like, again, calibration frames. I need to do a whole section on calibration frames, how to take them the whole 9 yards. It's one of those areas that I constantly see people trip over this.
Okay, so let me just show you that I removed that dark frame here. And so remember, I had flat darks checked. And so when I try to run this, it gives me this diagnostic message. It says, warning, neither bias nor master dark is found to calibrate the flat field images. It's not finding anything because all it's seeing is 180 second dark, and it has a flat that's 1.08 seconds, and I had flat darks checked. So it's complaining, look, I'm looking for something that's 1.08 seconds, and that ain't in the list, right? So that's what happens when you use flat darks. It means you're obligated to match them. Now I need to load those darks yet again because I removed them to demonstrate the error there. Here are the flat darks. Oh, did I miss? There they are. And I need to say that they are dark frames because this is just demonstrating a mistake that someone made, that's all. And I need to tell it the exposure time. Okay. So now they're in the column. This time when I hit diagnostics, it doesn't complain, right? It's happy. It says, oh, I can match 1.08 seconds with 1.08 seconds. Wonderful. It says no bias frames have been selected. Well, that's fine. We're not using bias frames. It's perfectly fine. And I haven't specified an output directory, which I think I'm going to be doing right now. So where am I going to put this? Geez, I need to find another place. So I keep
you haven't run out of space yet.
I know. I just have, because I do these, things all the time that I get things everywhere. I'm going to create a directory here called wood h, and that's where I'm going to put it. Okay. Now I got to be a little careful about what the heck I'm doing. Let me think. I'm not optimizing anything. We're doing a straight up subtraction. We're not using any masters because it's going to generate the masters here for us. What I do want to do for lights is we're just going to do calibrate only, right? We're just calibrating. That's all I need to do. And I'm thinking that is all I need to do. I'm not going to worry about cosmetic correction. You can turn it on, but it's just going to use up more time. So if I hit run, it should go. And here it goes. Now, this particular data set is really interesting because I'm going to do everything absolutely correctly, and it's not going to work. I'll tell you right now, it's not going to work. And that's actually the cool thing, is to understand why it didn't work. And then I can show another part of what makes CMOS sensors a little crazy, in my opinion. There are more vagaries to kind of look out for. And that's only virtue of the fact it's kind of new, right? They have their own behaviors that are different than CCD kind of behaviors. There are some, because of the electronics that are being used, it's a little bit different. So while this is calibrating, making master darks and whatever, do you have any, are there any other questions?
No, just people thanking the clarification. Okay. Like I said, that's why I kind of paused you there, because I know how people think on questions like this.
Yeah. Oh, what?
No, we did it.
I needed, this was not, I'm not using, this is supposed to be a monochrome thing, and I had the CFA checked. I don't think that's going to matter because it tried to debayer something that can't be debayered. So that's fine. I should have had this unchecked. That's all. Okay, I should have, that should have resulted in, though, calibrated data. Let me just show you, I hope. So that's here, and then wood H, calibrated, light. Well, debayered doesn't matter because it's no, there shouldn't be anything in here, right? Because it didn't succeed at that. So here is an example of a calibrated frame, right? Now, at first glance, this looks perfectly fine. I mean, it looks okay, right? I don't see anything terribly wrong with it. I do notice that maybe it's a little bit darker in the center. And this is one of the things about CMOS sensors that are different. Remember an hour ago, I mentioned that when you take CMOS data, typically people are taking very short exposures. The problem with very short exposures is that the signal, both the stuff that the sensor might be doing and from the light from the sky, is so small that when you visually look at the data, you may not be able to see there's a problem until you integrate all the data, and then you can see there's a big problem. And that's different than CCD stuff. So usually in CCD stuff, you can see when usually you can tell that something is awry, something is wrong, gone awry when you just calibrate a single frame. But because these exposures are so short, that often doesn't happen that way. So let me show you that if I were to, very quickly here, let's see. I suspect that I need to align these images. So we're going to do close files. We do, I was really hoping it shows up there. It doesn't show up there yet. Hopefully it will. Here we are, calibrated light, right? And then if I do here, register, I don't know why it's capital, registered. Oh. There. Oh, this needs to be a reference. Oh, God, I get so confused. That's the reference frame. These are the files we're aligning. I've just picked, all of this I'm picking randomly. Output directory, that's the one I just created. That's what I was working on. So that should be here, 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 right? And I think that's it. Go. Just do it. I don't need drizzle data. Oh, I forgot. That's another default I think is a little silly. But I have few enough frames. This shouldn't take too much time. There it goes. It's doing the, there, it aligned, right? And then once you have aligned images, what can you do? Well, you can combine them. So we do image integration here. And now we do add files. Well, I got to remove whatever this stuff is. Clear. Add files, registered here. Now the method that we're going to use is not critical as long as it works. Yeah, it's fine. Whatever. We don't want this. Just do it. Integrate. So this is the Galaxy. I don't know if anyone recognizes. It's M106.
You know, the funniest thing is Messier numbers mean nothing to me. I go by the name of the object.
The Canis Venatici M106. I don't know what you would call this. There are too many galaxies to have nicknames.
Oh, I'm terrible when it comes down to Messier objects.
Well, the catalog name is the nickname to me. So there's nothing special going on in the rejection here. Just ignore that. Here is the integrated result. And would you agree with me, now that we've integrated, that the error, I've only done a small subset of this, this person had like 40 or 50 of these frames, right? It'll only become much more pronounced with the addition of more frames. So this is a kind of flat error. This is exactly the thing I was talking about when you have what is basically an over-under correction of the flat field image. So if we actually look at the master flat, if I come back here and I go to masters and we look here at the master flat, you can see it's a nice flat field image. I don't see anything wrong with the flat. And I should also mention that if you look at the dark frame, I don't see anything wrong with the dark frame or even the flat dark frame. Here, visually, these seem to make sense. There's nothing wrong with them, right? But what I do notice is that it's darker here at the outside of the flat and brighter here in the inside of the flat. That's very typical, vignetting, right? But notice the integrated result is the exact opposite, where you have it bright on the outside and dark in the inside. So that's an overcorrection. It means that we would have expected this stuff here to have become not this dark, right? And this stuff up here, not this bright. It should have been to a lesser degree. So it's an overcorrection. So the question is, what's the problem? Where is this problem? And what I'm going to say to you is that whenever you see an over-under correction like that, of this particular kind, whenever you see that, that is telling you that there is something wrong with either the bias. Now I'm being very general here. In this case, we don't have a bias, but it's something wrong with the subtraction of the bias or the dark or the flat dark. There's something about the pedestal value that was added or subtracted from the image that made the flat not work. It's not that the flat is bad. When the flat over or under corrects everywhere globally, that's usually meaning the pedestal that was either added or subtracted in the course of calibrating the data, something happened there. Now, if you have a flat that's not getting, it's getting rid of the vignetting, but it's not getting rid of dust donuts, that's a different problem. It's not the same thing. So what I'm demonstrating here is a straight up over or under correction with a flat, usually due to the fact of there's either something going on here with the pedestal values being added or subtracted in the course of calibration. So when this person presented this particular issue, there are two ways of approaching it. One approach is just to brute force, find a way to make it work, which is what I'm about to demonstrate. Alternatively, what you can do is, do more detective work and try to figure out, there's got to be some way to figure out something's wrong, which I'll get to as well. But let me just show you a brute force method because it's just a lot of fun. When you have an over or under correction such as this, I'm telling you, we know that either the number of the pedestal value of the bias or whatever it was, the flat dark, we know that number was either too big or too small. Something was wrong with it. So what we can do is we can actually add or subtract a value basically to the flat to kind of compensate for that effect. And in that way, we can get a better result, basically just change the result. So that is kind of the idea here. Hang on one second.
Keep going. I just got to run to the bathroom.
Okay, that's fine. I knew that someone was going to need to take a bathroom break.
Well, they've got the luxury of pausing. I don't.
Okay, so what I'm saying is that you can take this flat field image here and you can add or subtract a number to it and then apply it as a new master and see if you get a different result. So I'm not going to iterate on this. I'm just going to show you the answer just to demonstrate that it kind of works. So let me just get out pixel math. But it's a neat thing to know is I guess all I'm going to say. I'm going to say target T plus, I'm going to do some crazy number like 0.3, which I think is too much as I recall, but whatever. So I just added a number and I'm going to save this as my new master. So I'm going to save this as a adjusted version there. And now what you'll see me do is get, I guess I don't need this now, WBPP back. And this time I have the flat, but I'm just going to use not this one. We'll clear this. But we're going to add the adjusted flat here. So the light frames are still the same. The dark frames are still the same. The output directory, and I want to be a little careful here because either I overwrite my files or I make a new set. So I will make a new directory. So this is going to be corrected. And then I think if I go, No bias frames. That's right. There is no bias frame. So I'm going to very quickly calibrate this data. It should go a little faster because it doesn't need to create the master flat. That was fast. Okay. Now, yes. Now I should have star alignment. So just to be super exacting here, we'll go into the same spot. Let's see, this is a reference frame there, but I need to make a new directory. So we'll call this registered there. So here's my reference frame. And we will add corrected, yes. We will add these guys together. And I need to put it into calibrated light registered. So all I'm doing is re-registering by creating the drizzle data, forgot again.
While that's doing that, I'm just going to answer a quick question on the chat.
Yep.
He's asking if he can get the name of that Photoshop plugin. There isn't one. You kind of have to do a method or follow a tutorial. I believe there is one up on YouTube, which involves StarNet++ to do the star map, and then you can kind of figure it out from there. Yeah,
I'm being a little coy. There is one. So,
oh, you're talking about Sarah's Astro Pack or something?
No.
Okay, good.
No, even better. So Russ Croman created a star reduction routine that is a plugin, and it does a very good job. So I would recommend you look up Russell Croman, and you'll find that he has a number of Astro utilities. He wrote it a long time ago, probably predates some of the people that are watching this in terms of their beginning astrophotography. I've been doing this a while, and so has Russ. So I encourage you to look that one up. So
resources. I'm just going to show everybody real quick on the screen. That's Russell Croman.
Yep.
And you'll get the idea of it. rc-astro.com, and you can figure it out from there.
Yep. So now I got to figure out where I was. So I've aligned. So now I just need to combine them, I think. So is everyone with me that all I did is I added a number to the flat? I added a pedestal number to the flat, and I just redid this. So I believe I can do the integration.
Oh, great. I had to go to the bathroom at the wrong time, didn't I?
No, yeah, actually didn't miss anything, but I just want to make sure you're still on track.
Oh, yeah, somebody's trying to post a link and you can't because it's turned off. Hold on. Oops, rc-astro.
I feel so proud I know stuff like that. Russ's thing.
I only know of him as an imager, not as a person that has
he
tools.
did some cool stuff. Check it out. Now that I've added a number and integrated the files, now we get a result which looks much better. So let me show you that. I'm going to go back to my, this one. No, I got to go there. I was hoping. So that is in here and here. Let me just show you the difference between, where's good? Here's good. Oh, I wanted good and bad. So here's what it looks like before I added that value, which is here. And this is adding the value here. Isn't that cool? So just by, this is the brute force method, just by adding a little bit to the flat or subtracting as necessary, you can correct for a small over or under correction. So if you just find, that you might not be able to find out why, even if you do have, you might have the correct bias in dark, maybe you tried to optimize whatever it is, that flat still is undercorrecting just a little bit, you can moderate the flat itself by adding or subtracting a small value and get it to bend to your will. And that's what I'm trying to demonstrate here. I hope everyone can see the effect is pretty dramatic.
Oh yeah, no, it really is.
Now, that being said, the correct thing to do is, of course, in this case, make sure that the calibration data was working. So I'd like to show you the detective work that I did to find the answer. Let me show you those master darks again. So here we are. I hope that I am doing this correctly here. So here's a master dark. I really have to be sure. Well, okay, I know what I can do. I'm going to go to my, I have to be sure I'm doing this here. Yeah, these masters I know are the bad ones, if you will. They're not bad, but something's wrong. Okay, remember I showed you the flat dark here, and here is the, let's see, which one's it? And this is the 180, no, this is the flat dark here. It says 1.08 seconds, and this is 180 seconds here. Now here's what I'd like you to notice. If I put my cursor here and we just look at a typical value, as I roll my cursor around, you see the value in 180 seconds. What does it say? It says 0.0037, 0.003, right? Now, in 1 second, this says 0.011. That should blow your mind. And this is why I am forever tainted as far as my opinion of CMOS sensors. What the person that made these calibration frames did everything correctly. Why did the behavior of the chip change? Why? I don't know. That's bizarre. This number should be bigger. It should either be equal to or larger than the number here, because this is 180 seconds. The minimum it could be is exactly the same as a 1 second exposure. It can only be that or larger. It can't be a smaller value. There's no way a dark frame of a longer exposure time can be a smaller value. That's the detective work. That's what told me this calibration data is no good. There's either the dark frame or the flat dark is bad. And I couldn't say which one, but this person did go back and take another new dark frame. And it turns out that when the person did it, that the value was also very nearly and a little bit larger than this, 0.011 or so. So it's like 0.012, 0.013, whatever it is. But it was then matching what we have here, something close to a flat dark, which is what we would expect. So this, for whatever reason, in the course of a few months, the way that the chip was behaving changed. And it wasn't a change in gain or anything like that. It just changed. Now, yeah, I don't even know. It was the same temperature as well. I have no idea. That's too weird a problem to have. You just can't have detectors misbehaving like that. That will make you pull out your hair. That's my tainted opinion of that kind of behavior. But does everyone see what the problem was? Simon, is that?
Oh yeah, totally.
You see that should make your head blow up? Okay, because when I saw these two values, I'm like, that doesn't make sense.
I'm going to say this. I've come across this with a lot of customers who send us, and they usually identify the fact that there must be something wrong with the camera. You know, if it's not them and it's not the way they're doing that, it must be something with the camera. This is the fun part of it. Again, this is when Richard Wright comes back, we will be doing the CCD versus CMOS debate, for lack of a better description.
Right.
But this is where value over performance is a critical factor. So many of these issues have been long since solved when it comes down to CCD. But when you're on a budget, which I do totally respect, a lot of people are on a budget, with the CMOS, there are ups and downs that you can come into. And I've had this exact same problem with the 183, especially with the amp glow, that it would never calibrate out. And what you did is not so dissimilar to how I solved the same problem. Is I have a set of master flats that I've taken from a very long time ago that will calibrate out, and then I'll take some new flats and darks, but nothing changed. Same exposure, same scope, same everything, but they won't calibrate out.
Yeah, and so my suggestion is always when you are collecting data, you know, make it the shortest amount of time possible between collecting data, either before or after, whatever it is, to collect everything that needs to characterize the system, be it the sensor or the optics, you know, as far as flats are concerned. So, you know, don't. Sometimes people rely on libraries of things, darks and flats, but whenever you're having an issue, the immediate response is make sure things are matching without any optimization, without any, you know, extra whiz bang stuff, and shorten the amount of time between when you did something and when you did something else, so that you know that everything is consistent and characterizes the system as closely as possible. And that will usually weed out a lot of problems, or at least identify where a particular issue is. Just as an example, one of the problems that I had when I would use an RC telescope is that it's an open truss. And so I could take flats at the beginning of a night, right? And then I take my light frame data, or I could do the inverse. Let me just say the inverse. I could take my data, and then in the morning I would take flats. And the funny thing would happen is that in the beginning of the night, I might have taken 10 exposures. And then a new little piece of dust just falls down from the sky, maybe 2 pieces, falls down from the sky, right through the little baffle in front of the sensor, you know, the baffle of the telescope. Well, it has a baffle. And it goes right onto the filter, and it sits there. Now, when I take those flats in the morning, the flats in the morning are going to characterize the system with the new donuts, but they will not correctly flat out the first 10 frames that I had before the dust had fallen onto the chip. And so there was no way around that. I mean, what can I do? Unless I sit there and take flats every 5 minutes to characterize the system, because there's dust flying around and falling onto my detector. So that's kind of the worst case scenario as far as dust is concerned. But yeah, doing the shortest amount of time you can to characterize the system in terms of either the sensor or the optics is a very diagnostic way to figure things out.
Real quick question: what is that inspection tool? I knew somebody was going to ask that.
Inspection tool? Which inspection?
The one that gives you the numbers.
Okay.
It's like a default thing.
Wait, that's an easy question.
Yeah, I was going to say that's like the default thing in PixInsight. That's the funny part.
Yeah. So down here, and this may go off the screen, but there is a probe, and then there's a readout mode, readout data here. So you can select different things that you want to do, but when you turn on the probe here, it will give you the in the preview, let's see, preview size. Yeah, you can select these guys, and it'll, when you just click the mouse and click on it, it will allow you to see, when you have this thing checked here, see the numbers. See, it says readout mode. So you have this little guy checked here, and then you set whatever you want in terms of the size of the probe and the 3 pixels or whatever. And then it'll give you the readout. Just make sure you click this guy right here, this little icon.
So he's asking, what does the K value stand for?
That's the brightness. So K is the
luminance,
the lightness. Yeah. So because this is a monochrome picture, we're not going to see RGB values. If I had an actual color picture, then it'll also show the RGB. Let's see, can I?
Yeah, it just gives you RGB values.
It gives you RGB values. I can't find right now one. I'd have to go find one. But yes, it gives you the RGB values. I don't know what this is. Oh, that's not it. I don't know. Okay. Yeah, so that's what you do. That gives you the readout. Very useful, right?
Very. Believe you me, that's how I solve problems sometimes.
Oh yeah, yeah. You're able to do that. So what would you like? I still have one other thing. It's not very exciting, I have one other thing that I can demonstrate. But I'm also happy to end here because this is perfectly endable.
Well,
It's been 2 hours. It's been 2 hours, so I just want to be sure.
Chris isn't due up until 4. Well, let's rephrase this. Mike Barber is coming on at 4:30 with Chris Go at 5 o'clock, if that makes sense. So, like I said, that's why I said there's no time limit for you. Because I actually had a bunch of crap prepped up in case you ended early and we didn't have dead 1 hour.
But what by your definition would have been early? That's my question. 4:30? Anything before 4:30 is early?
Yeah, I've got things to fill time slots by blocks of 15, 10 minutes, 15. I've got even an hour space filler.
Well, I tell you what, let me do one more thing. And if there are any other random questions that, that I can answer on any topic in PixInsight in this case, I'm happy to.
Well, actually, I will have questions for you at the end. So don't feel that you don't have questions. I've got questions.
All right. So let me show you one more very brief thing that I think is kind of cool. Because just another example of one of these things that I get from the forums. Now I have to think for a moment where this is. This is, I believe this is in my I have this, one of these, I believe I have this as a, one of my YouTube videos. So I have to think, hold on. This is in video recordings and probably office hours, right? PixInsight, office hours, hot pixels, I think so. Yes, here. And okay, let me just open up this frame. So one of the other things that often happens with CMOS, again, sensor things, and it's not a function of the sensor per se, it's more a function of its usage. As I've mentioned a number of times now, people tend to take these very short exposures, and that leads to other kinds of issues. So one of the big issues that I see on these forums is that people, maybe I should look at a debayered image, sorry, let's look at a debayered image. People will take a set of frames, debayered, oh gosh, I have different, it doesn't matter, let's just do one. Set of frames, and they will try to align them. I guess I should do, so you don't have to look at a purple mess here. There. Very short exposure, right? You can barely see a cluster here, but there is a globular cluster. And they'll take a bunch of these frames, try to align them, and fail. But it's worse than that. And what I'll demonstrate here in a moment is that you try to align them using star alignment here. You try to align these frames. And what inevitably happens is that it shows that it aligned them. When you look at the console, at the end of the day, at the bottom, it says, whatever number of frames aligned, no problems, no failures. And yet you blink the images and they're not aligned. This happens all the time with CMOS sensors, especially because of the short exposures. And what is going on is that the signal for these stars is so small that hot pixels that are in the frame are actually brighter than the stars themselves, so that the detection algorithm for what are things that are stars in the image in star alignment picks up on the hot pixels and not the stars. And that is not obvious at all, because the hot pixels, they don't look like big. I mean, by eye, you would just never think that there was going to be a problem because they don't look like a star. But the problem is that to the algorithm, they look more like stars than the stars do themselves, because the stars are not bright and they're smeared out among many pixels, where you have these bright little things in there which really do look like stars. And so the trick usually is with this kind of data to remove the hot pixels. Now, hot pixels, especially again with short exposure CMOS sensors and so on, may not entirely come out with normal calibration. Not every single hot pixel, certainly not cosmic rays, they're not going to fall out from that. And so you're almost always going to need to use cosmetic correction in order to get rid of those hot pixels, so that later on in processing, you don't run into all these other problems like registering the images. So let me see if I can demonstrate all of that for you. What I really want to do is, it's going to take me one moment here to look at this, because I want to do this in as quickly as possible. I should have just straight up calibrated data. That's what this is. This data right here has been calibrated, but it has not yet been debayered. And this data has been calibrated. You see, I have a calibrated and cosmetically corrected. That's the right result. But let me show you a calibrated and just debayered, which I think is this one. So I don't really need to demonstrate creating that. I just want to demonstrate what things look like. So this data, yes, thank you. This data has been calibrated and debayered, but no cosmetic correction. And that's often where people trip up. They just don't, either they don't know about it or think it's important, or maybe don't use it properly or things like that. So this little guy right there, that is a hot pixel. There is also, well, there's one. There's a hot pixel there. And there are other hot pixels. But you'll notice this is a debayered image. Here, let's see, there's one. Here in the debayered image, these hot pixels, they're not a pixel. They are actually many pixels. That's not one pixel. It used to be one pixel in the original raw data, but it is not a single pixel here. So let me show that to you. If we look actually at the raw data, let me look at raw data, which is here. This is the absolute raw data. So we're going to see the, the crazy grid. But if we come over here, here's a hot pixel, and it actually is a single pixel. So when the debayer process occurs, let me get up debayer. There are two different methods of debayering. So you would load target images and all that. But here is the debayering or demosaicing method. Well, maybe three methods, but the other two are synonymous. So we have a superpixel method, which I would call extraction. And then we have the default, which is VNG. The VNG default, the way that the debayer occurs is it takes the Bayer matrix of, say, a red pixel or green pixel or blue pixel, and it looks at the surrounding neighboring pixels in order to interpolate and put in a value where in between where one red pixel is and the next one is. Because when you, if you're trying to keep this image the same size, you have to interpolate between the values. Maybe I should show, I'm not really showing what I need to show here. Bayer matrix. There's one. That's good enough, I guess, right? So if I were to keep the image the exact same size when I debayer it, this is actually the pattern that's on the chip, right? You have red, green, blue, and these little quad squares. Oftentimes what happens is you can average the two greens and then you do something with the reds. What you can do is you can actually just extract that information. This is the superpixel method, where for every one pixel, you would take this group of 4 and you convert it to 1 pixel. So this group of 4, we would convert to 1 pixel by averaging the two greens, whatever that number is, and then we have a red, green, blue number for a color value at that 1 pixel. And then we go to the next group of 4 and we do the same computation and go to the next group and so on and so forth. So we're going to end up with an image that is half the size of the original image, because there are these spaces between each of the colors, right? We're not using those spaces. But in the VNG method, we're going to actually keep the image the exact same size. And where there's a green pixel here, we have to figure out what to put there when we're looking at our red plane. The red channel, we have to decide for all of these green and blue pixels what values of red we put there. And the VNG method uses some special algorithm to do math and figure out what values to fill in these regions of the chip with red information. So that maintains the size of the image, but it also does an interpolation, a smearing, and that smearing directly affects what happens to these pixels where they used to be one, they suddenly become more than one because of that process. And the thing is that at this point, once you've debayered, you can't use cosmetic correction. You have to do cosmetic correction. You have to remove the hot pixels before you demosaic or you debayer the chip, if you're using one of these interpolative-like methods of debayering. So that's the fundamental problem. And I would like to demonstrate that it really, really doesn't work. That is a fundamental problem. So let me show you cosmetic correction here. And I believe, let's do it this way. I'm just going to draw a little preview here, make things really quick. Zoom in. And if I do a real-time view, right? Can I do that? Maybe I need to choose a map. Probably won't do anything because I haven't chosen anything. Oh, that's better. Okay. So I'm using auto detect. This is trying to remove this hot pixel. I'm putting quotes here, this hot pixel, based on a sigma value. But the point is that no matter, you can see other pixels there disappearing, right? No matter what threshold I choose, it's not going to get rid of this thing. You'll notice if I turn it off, the center that was kind of a bright white, it gets zapped a little bit, but the thing doesn't go away. The thing is still the same. Now, I'm going to, just to make sure that that's clear, I'm going to put the same preview in this image here. So it should find the same little hot pixel, right? And now, if I do my little real-time thing, you'll see that it does get rid of the hot pixel almost at any of these crazy values, because that pixel really is very, very much different than all the surrounding pixels. Now, here's the weird caveat, though. To make cosmetic correction work properly, you need to tell it that you have a color filter array. And the reason for that is that it has to do this calculation of whatever value. This could be a red pixel, this could be a green pixel, this could be a blue pixel. But whatever calculation it does, it can't be based on only the wrong colors that are surrounding it, because none of these things that are surrounding it are, let's say it was a red pixel, none of them are red. So it won't be doing this correctly if I don't tell it, hey, this is a color filter array. What this is actually doing for the calculation, it needs to figure it out by doing the super pixel internally. Internally, the way that cosmetic correction works is it does the super pixel extraction, if you will. Then it can do the rejection of this cosmetic correction of the hot pixel. And then you get to interpolate your image and you won't have any of these problems. Okay, so I've demonstrated now how cosmetic correction works. I'm going to close this. Let me just demonstrate the issue. The issue is that if I take star alignment, I'm going to clear, well, I'll just overwrite, it doesn't matter. I'm going to go to that directory. Now that directory was, I really wish it was up there. So that directory is PixInsight, no, not there. It's video recordings. Everyone's going to know my directory structure soon. PixInsight, office hours, hot pixels, and we have here debayer. Well, I did a small number. Well, that's probably fine, a small number. Let me think about that. So these have been debayered. These have been registered. Right, debayered. Well, let's go back to the directory that I had, though. So the directory that I had was, because I've done this so many times, right here. Yeah, here they. Let me think. There. Okay. So these files right here that I am highlighting, these have been calibrated and debayered. These are the things that normally someone, and this is what happened with this individual, would try to align these images. So I'm going to pick one of them. And then I'm going to pick a few more to align. I don't need to align them all. So I will pick this one, this one, this one, this one, this one, whatever. This one, doesn't matter. So I have a reference frame. I have a bunch of frames. All these are calibrated and debayered. Those hot pixels are still in these frames, and they've been blown up a little bit. So I need to tell it a directory, and I'm going to go put this in some odd place. Sure, I'll put these here. Why not? And then I say do it. And hopefully this is going to demonstrate the issue, and then I'll demonstrate the solution, and we'll call it good. Now, for those that are really super observant, as these numbers click by here for transformation matrix, it is actually telling you there's a problem. So notice that at the bottom here, this says 6 succeeded and none failed. If you just read the bottom line, you would just think that, well, there's no problem. And then what happens is that people would come to Blink and they open up those files, which I put in this funny place. I put them here, here, and here they are. And I've got to hit this button so that it doesn't look like a purple mess, right? And then we blink through the images. Would you agree that those files are not aligned?
Oh, they're perfectly aligned. What are you talking about?
Okay. All right. But again, I want to just look, it says it's aligned, but they're not aligned. That drives people nuts, right? That's the kind of thing in software where you think the world is just not in order. So it is communicating to you, though, that there is a problem. Notice in the transformation matrix, which means how much did I have to shift, translate, rotate, whatever it is, these images with respect to one another. Look at the numbers. It said it had to do 0.01 pixels. 0.01 pixels, I can see these pixels, these images. I know these images are dithered more than 0.01 pixels. I know it had to have calculated an answer bigger than that. In fact, those numbers are so close to zero, it is zero. So what in the image would it have been aligning on that would not have moved? And the answer is, of course, the hot pixels. Now, it doesn't say that it was aligning on hot pixels. Nowhere does it say that. But you can infer that from the fact that nothing was being moved. Nothing was moving at all. You would expect that if it was a noise, it might be crazy. It might not be aligned, but it might be crazy values everywhere. But that's not what we get. It get that it was trying to do this alignment exactly with no shifts. What is that? That means something is static in the image that it's aligning on. So now we will do this. And all I'm going to do this time, I'm going to save some time. I'm going to say that I have run now cosmetic correction in the proper way by checking the CFA box and by assigning a threshold of sigma, as I demonstrated a moment ago. All I will have done is done cosmetic correction and then debayer. So I'm going to, let's see. I need to go back to the skits. I'm going to keep track of this. So this is in the other place. PixInsight, no, not there. Video recordings, PixInsight, office hours, hot pixels. And I went into here, 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 here. Yes. So these files are the ones that have the cosmetic correction. 1, 2, 3, 4, 5, whatever.
Hold on, you got one that wasn't there. There's a D.
That
yeah,
one?
Yeah.
Thank you.
Get rid of that bastard.
Thank you, thank you, thank you. That would screw things up. Okay, and I will put them, let's see, is it going to I don't know what it's, no, it's not going to overwrite. I will see them because it has an extra bit. So I will just do this. Now, if we look in the console, as it does the alignment, we should see 2216, yes, translations are occurring. Those are not 0.01. Those are real numbers. Now, this time it said this, apparently I did one less, but the star alignment succeeded. So I should be able to go back to, is Blink here? Blink is here. Come back to here. And I go to, I go back to D, I go to here, and then you'll see that the ones here that have the extra bit, 1, 2, 3, 4, 5, do this button. Couple of things. One, if we just scroll over to where some of those hot pixels were, now you won't find them. You won't see the hot pixels. They really are gone. And that helped this process because now if I blink through, the images are aligned. The only difference was the removal of the hot pixels. Now, there is a brute force thing that you can do. I'll just mention this, but it's not the right thing to do. You can screw around with the star detection algorithm, the innards of this algorithm and what it considers a star. And you can force it basically here to ignore hot pixels. That works, but that isn't in general the way to handle the problem. The way to handle the problem in general is to remove the hot pixels beforehand. And this is something that I see continually crop up with people that are using CMOS sensors. It has nothing to do with the sensor other than the fact that people's exposures tend to be short. And that means that the signal for the stars here is very low and hot pixels are brighter than stars. And so hot pixels tend to dominate in terms of something that you need to consider or deal with, where that might not have been the case with a CCD camera, where many of these other signals dwarf the effects of hot pixels. So that was my last example of CMOS things to consider.
Marvelous.
Yep.
Okay. Let's start with the sales pitch. So for those of you who are interested in Adam's tutorials, and I do highly recommend that you do some of these things, do you want to just fire up your site real quick so people can see it? Because we can go through that with them. So if you're a newcomer and so forth and so on.
But, again, Simon, I would say that, let's say you're not a believer. Let's say that, there's so many free YouTube's videos or whatever. Go to my YouTube site and look at the free available stuff that I will continually post material there because I'm obviously trying to feed people into my paid content. But I do try to make available content just freely in YouTube. And if you like what I do there, you'll really like what I do here.
Okay, so, but let's go into this side of things, because some people may not know what part to buy.
Oh, so I have, so on my site, there are 2 different parts for PixInsight anyway. There are other software programs. PixInsight. I have fundamentals, which basically I say, if you're interested in learning PixInsight at any level, you really should just get fundamentals first. The Horizons, which is another library of content, quite a bit of it, is a continuation of the content of the material that I do in fundamentals. In fact, it builds on it and assumes that you've already basically seen that material. When I say fundamentals, it doesn't mean that it's novice material or basic. All I mean is that it is fundamental to the art and science of image processing. And then in Horizons, one of the nice things about Horizons is that in addition to other videos where I demonstrate certain things, I also make available data sets where you are presented with high quality, by the way, data sets. Some of this stuff this is from Telescope Live and other things, and 32-inch telescope. So nice data sets, as well as data sets that are not so perfect. This data set here is from Detroit. So people have sent me some examples from all over the place. But you get the data, you get to see me go through it in real time without any varnished, polished anything. And that may be something that people enjoy. Sometimes, you get to see everything. So it might be like, come on, get on with it. But that is what image processing is like. If you see only when it's done correctly, you miss out on a lot of things that can be learned. So I demonstrate that in my Horizons area, in addition to the other, just additions that I do for new things that I've discovered or innovations or whatever they might be.
So now the next thing would be, not everybody has PixInsight. So majority of people have Photoshop for whatever way they get it, buy it, whatever subscription. Some people even still use older versions of Photoshop, depending on how you purchased it. Question is, how do you cater for those guys?
Well, I do have material on Photoshop now, given what I described earlier, where I began this road of learning PixInsight, basically 2014 or 15. My last tutorial dates of that time on Photoshop. Now, everything that I demonstrate in Photoshop, the techniques are still valid in terms of what people would like to do. I mean, I explain everything you need to know about layers and masks and all of that kind of stuff. So all of that is within the Photoshop realms here. But it does date back to 2015. So there are obviously going to be things within Photoshop today, and it's 5 or 6 years later, that would not be represented in what I demonstrate in my recording in terms of where some buttons are and certain things that are new features. But the techniques are valid, and it's a nice thing to know that if anyone wants to check out my Photoshop stuff, you could do that as well.
So I'm going to throw down a challenge for you, and I'll be curious to see if you can do this.
No, I can't, because it's comparing apples and oranges. But go ahead. Let me. What's the challenge?
Processing an image using only free software. You knew where I was coming with this.
Yeah. Well, that was actually, I thought you were going to go a different question. I thought you were going to ask me to process like only in Photoshop or something.
No, in only free software.
So I personally, because I have spent so much energy in trying to wrap my hands around something like PixInsight, for example, that I am not proficient, and I wouldn't want to do that unless I felt proficient in any program, whether it was free, paid, whatever it was. So the short answer to the question is, it's not a very good answer, but I couldn't do it right now because I'm just not proficient in these other softwares. If I were to become proficient in something like Deep Sky Stacker or whatever it is, then sure. I mean, I could obviously speak to some of the tools or techniques that might be more amenable in one program compared to another. One of the traps, though, that I do find when comparing softwares is that, as far as the math is concerned, unless there is a fundamental bug or error, there is no program that's going to somehow add or subtract or divide or whatever it is better than another. That isn't where the game is. It's instead some of the algorithms, which are a combination of this math, might make it easier or more difficult to do certain things. And there may be some algorithms that only exist in one package and do not exist in another. So those are the places that the differences lie. Sometimes people are talking about, one program can calibrate better than another. Typically, that isn't the case, because the calibration process is literally adding and dividing, adding and subtracting and dividing. There's nothing there to do. But when you get into the more complex operations, where you have many different operations, then there can be differences in either the way in which you use the program, the kind of technique that's used, or there may just be no example in one program compared to another. So, I mean, that used to be asked of me when comparing things like, PixInsight to the old methods that I would use, which was a combination of CCD stack and Photoshop. So, for example, there is no between the combination of CCD stack and Photoshop, there's nothing really like DBE. There's nothing really like HDRMT. I mean, and those are algorithms which are, just really something that PixInsight that I could do that I couldn't do in the old method. So that would be a good point of comparison in that sense.
Definitely.
Yeah, but I haven't done I haven't done all the free software. I mean, you only have so much time in a day.
Yeah,
I've done a lot of software.
It's a challenge that some of us basically do. A lot of the times I do use all the free software because I have to think along the lines of the newcomer. Some of the really crazy advanced stuff, people don't know that I know the advanced stuff because it just looks like I just know basic shit. But the reality behind it here is I choose not to tell people about the advanced stuff because I generally don't get those types of phone calls.
Well,
it scares people.
Well,
I need you.
My take on education, which is kind of a different topic. In other words, how do you explain and teach or demonstrate ideas or concepts? The way that I approach this is different than many other people in the sense that I tend to be verbose. I tend to explain a lot. But the reason that I'm doing it, it's my style, is because I'm not so much interested in giving a recipe. I am more interested in making certain that the concept of what you're doing makes sense, because then you can look at any software program and potentially figure out how to use it, because you'll understand the language or the idea behind something. And in addition to that, and this is the really big one, because there are so many different parameters and things that can go wrong, the fundamental thing to be able to do is to be able to solve your own problems. And that is the thing that I teach. It isn't so much the step-by-step. It is understanding what to do when you have a problem based on the information that you learned or that you practiced or whatever it is. So that's where I really come from. And that really does affect strongly the way in which I approach teaching the material. And it is different than other people. So I would encourage people, please look at my YouTube videos so you can see what that style looks like. And I think it's very powerful.
And I'm just going to add to that real quick. A lot of people out there watch tutorials because that's the name of the word, tutorial. They're taught how to walk through a door essentially, but they're not told what the door handle does or the hinges on the door or the door itself. That's the interesting side of things. So usually when I try to teach people, it's a similar situation to what you're doing. I don't tell anybody a group of steps. I show everybody, these are all these buttons. What do each button do? The idea here is once you know what that button does, figure it out on how you want to achieve a result. Because by knowing what the buttons do, you know what the end result should be.
Right.
Because too many times have I done a tutorial or done a course or whatever, and somebody follows it verbatim, literally word for word, and goes, it doesn't work. And I said, well, hold on a second. What scope are you using? What are your settings? What time of day? So forth and so on. And none of it's going to match what I'm doing unless you're standing next to me with my scope. But they don't realize that everybody's situation is unique. And the idea here is we learn a set of tools. And hopefully this is what we do here with these live streams. We're not showing you too much of do this, and that equates to this. We're trying to show you the set of tools that you need in order to give you that final result.
Yeah. So I totally agree with that. But then there's the other thing, and I just want to say it again, a lot of people will look online and they'll find what someone said. And unfortunately, sometimes it has consequences, because sometimes people say something and it becomes a popular thing, but
seen it, been there, done it.
Yeah, it follows, and it's not that it's wrong, but it may not apply in all circumstances, and appreciating that becomes important. And then there's the other thing that I mentioned earlier, which I think is just so important. I'll just say it again. Defaults are illusions. I'm telling you. There is nothing special about defaults, usually. In order to take it, here's the key. In order to take advantage of a default or to take advantage of anything that is automatic, you have to actually understand it in its entirety, whatever it is that you're taking advantage of, so that you know it's either doing it correctly or what to do when there's a problem. And so you really can't take advantage of an automatic thing or a default until you really understand all the stuff that's kind of behind that. So defaults are illusions.
I totally agree with you on that one. I really do. I kind of liken it to driving a car. I learned how to drive manual or stick shift, whatever you guys refer to it as.
Yeah.
When I drive my cars, because most of them, if not all of them, are automatic, my biggest thing that I hate is this thing doesn't shift when I want it to shift.
Oh,
It drives me berserk
yeah.
because it always does it at the wrong moment.
Huh.
So prime example of default not working.
Yeah, okay. I guess having always driven an automatic, I just let it do it. And I, of all the places, I guess I have failed in that area. So that's interesting.
But again, it's a method and a teaching in that sense. Is I gone out of my way, and I apply this with everything. I go out of my way to understand what it is that this, whatever it is doing before I go off and utilize it, because I now drive in a very specific way to control the shifting on that car. Just like when I do my solar imaging,
Right.
I don't just hit record and walk off. I sit there very specifically and wait, and I watch the screen and I wait for the atmospherics to slow down. And when it does what I'm looking for is when I hit record.
Sure.
So I'm not wasting frame after frame after frame. And that's what a lot of people I've noticed, even with deep sky imaging, you've got all this automation software. It's fantastic. It's great. But they set it up, they press that button, and they go run off and go do something else. Yeah. I still sit there and watch every frame come down. I'm just stupid that way.
Yeah, no, there's still an optimization that can occur there, because if you're not watching, then I could be looking at clouds for 5 hours, or maybe the sky is half cloudy and you could just point somewhere else and do something. Yeah, so you never know. So, Simon, is there anyone still? Is this a conversation between you and me, or is
no? There are actually people still watching. I know it's hard to believe, but there are still people watching.
It's hard to believe. Well, but I'm not going to impose anymore. So I really appreciate the opportunity to do another.
No, I appreciate your time more than anything else, and I think people at home appreciate the fact that you spend so much time out of your day to go through things like this. So, needless to say, Adam will be back. There will be specific topics that I'm going to hand to him to do talks about. Like I said, this was a little unplanned for him to be around today, but
completely. Let's just say this, completely unplanned. So I didn't practice any of that. I just whatever. That's what I just did.
Yeah, but I do have set topics that I do want Adam to talk about, and I know this is his thing. What's this? I can't. Okay, so somebody's actually giving you praise here. I can't recommend Adam's courses more highly. PixInsight Fundamentals is great, but Horizon gives full processing examples, which have given me new ways of solving problems.
Cool.
So I think word of mouth is your strongest ally here. But again, if you guys do want to know more about Adam's work and check out his videos, start with his YouTube channel. Make sure you subscribe, check out some of his stuff. He really does appreciate you doing that. And once you get your head around it and you're ready to move on, start with fundamentals. I highly, highly recommend what he does there. I've seen some of his stuff. He's probably going to wonder, how did I see some of it? But I've seen some of it. And put it this way, you can learn tons from just 10, 15 minutes of any of his videos, to be honest. So Adam, thank you very much.
Thank you.
Hopefully we will see you again soon.
Okay.
All right, guys. We will be back at around about 4:30. Mike from QHY is going to be on for a very quick announcement, and then followed with Christopher Go. So we will be back at around about 4:30, and I'm going to go get something to eat. So we will see you guys soon.